Oh, okay. All right. Today we're going to be looking at the properties of gases, and some of this I think you probably would have seen before if you had a good high school course, particularly about part of it that we're going to do. We're going to um, look at gases, and there are a few of the elements on the periodic chart that are gaseous. Um, Hydrogen at room temperature in elemental form. Hydrogen is H2, oxygen is O2, nitrogen is N2, fluorine F2, chlorine Cl2, and of course the noble gases, helium, neon, krypton, xenon, and radon, are all gaseous at room temperature. Um, just along those lines, the vast majority of all the elements on the periodic chart are metals. Um, there are um, and almost all of them are solids. Um, there's actually these gases and two liquids at room temperature on the periodic table. I bet you know one of them. One of them is a liquid metal, and you probably know mercury is the only liquid metal. You might not know, but um, the liquid nonmetal is at room temperature is bromine. You notice I didn't include it in the fluorine family. Fluorine, chlorine are gases at room temperature, but actually bromine is a liquid at room temperature, and iodine is a solid at room temperature. So almost all of them are solids, and of the solids, the vast majority of them are metals. Okay, but these are the gases at room temperature. There are some common gases that we generate in the laboratory or in natural environments as well. Carbon dioxide is a natural component of our atmosphere. Carbon monoxide we make if we incompletely combust anything containing carbon. So if you burn carbon compounds in a limited amount of oxygen so that you don't have quite enough oxygen to complete the reaction, you'll make CO. And CO, of course, is extremely toxic. Um, it, um, it, it's a good reason you ought to have a carbon monoxide detector in your house. It's colorless and odorless, um, and it's usually formed in the smoldering stages of burning. So if you get a house fire or something, especially right in the beginning and the smoldering part of it, you might get some carbon monoxide buildup. And it turns out that the your nose is in the part of your brain, the sensitivity for smell is in the part of your brain that sleeps. So if you go to sleep, uh, you don't smell. So you wouldn't smell odors and things. You wouldn't smell the fire. The only thing that saves you is that if you get a cough reflex, so if there's smoke in the room and it makes you cough, that'll wake you up enough that your nose will then detect the smell. So that's why a lot of people die in fires is it doesn't produce enough smoke, but it's produced enough carbon monoxide that by the time the smoke gets thick enough, then they're already passed out. So it's really a good idea to have a carbon monoxide detector. Nitrogen dioxide, nitrogen monoxide, ammonia. You're more familiar with ammonia and the aqueous solution uh, in labs, but ammonia itself at room temperature is a gas, and HF HCl. HCl, aqueous solution, is our hydrochloric acid, but it is a gas at room temperature. HBr, HI, H2S, SO2. These are some common laboratory gases that you could make in the lab easily. And one of the characteristics of gases is that they can exert pressure. And we have a concept of what that is, but pressure is defined as force per unit area. So every little piece of surface area has a force exerting on it, and if there's gases around, and the pressure that the gas is exerting is defined by the force divided by the area that that force is applied to. Now, force is going to be in newtons, and area is in meters squared. Remember, those are our basic SI units. For force, it's called a newton, and the area has to be in meters, so it's newtons per square meter would be the SI unit for force. Newtons per square meter is a pressure unit that's called Pascal. You may or may not have ever heard of that pressure unit before. So the way we would measure pressure is we would measure the force and divide by the area, and that would give you the pressure. Now, the way we express pressure is from Newton's second law, that the force applied to an object will cause it to accelerate in the direction of the force proportional to its mass. So F equals m times A. A is the change in speed. Speed is meters per second. So change in speed would be meters per second. Mass is in kilograms. So these would be the units. It would be kilograms meters squared per second. Meters per second squared would be the force. So we apply a force in the direction that we want the object to move. And the object will not only move if the force is greater than the resisting force, but the difference between the force you apply and the force of resistance is the net force that's applied to the mass. The mass will not only move in the direction of the force, it will get faster and faster and faster in proportion to the force. So it's an increase in the velocity. So in the MKS unit, we said unit of force is the Newton, and it's kilograms meters per second squared. And that comes from F equals ma, a very Newton's famous second law. Unit of pressure, we said, is Pascal. So that is going to be newtons per square meter, would be that. And if we put in all of those units, you could deconvolve it. I want to tell you something right up front again about units. If you keep your units straight, carry them with your calculations, and make sure the unit that you come out with the answer is the unit you want from the problem. If you get the units right, you're going to get the problem right. So the units are really, really important. Now, these, if I say, okay, a Newton is a kilogram meters per second squared, and Pascal is a Newton per square meter, then it's a kilogram meter per second squared divided by blah, blah, blah. The important thing is keep everything in SI units. So if I've got an equation that on the left side, it says M equals something, mass equals something. Well, if I put all of those things in the right-hand side in their proper SI unit and do the math, my calculator will give me the number. It won't give me the unit. But if I've calculated mass, that number on my calculator is kilograms because I put in SI units on everything on the right. if I've got a distance like L equals something, and I put in the units on the right of that equal sign in SI units, I don't have to deconvolve those units. I can be confident if I put SI units on the right, I get the SI unit on the left. So if I'm doing length, that length is coming out in meters. So when I get a number on my calculator, I know to attach meters as the unit for it. So it's important to know what the SI units are, and that's way, way back in lecture 1. There's a little table there that has a listing of all the SI units. And all right, now, this is a really interesting number. If you think about atmospheric pressure, it is really the atmosphere, the force that the atmosphere is exerting because it has a mass. And the force that it's exerting on a square meter of area would be the pressure in pascals. And it's determined by how much that atmospheric pressure weighs. Well, this is the weird thing. If you took a 1 square meter area, 1 meter wide by 1 meter long, 1 meter long, and added up all the mass of the air that's sitting on top of that meter, it's almost exactly 10,000 kilograms. I mean, that is so amazing to me that you just think about it. The weight of the atmosphere is 10,000 to, I think it's to at least 3 significant figures, if not 4. So this is that's the mass of the atmosphere. And if you multiply the mass times the acceleration constant for gravity, it's 9.8 newtons. So then you add this all up and you get the 1 atmosphere pressure. It's about 100,000 pascals, or 100 kilopascals. So it's not exactly 100, it's 101.3. So if I wanted 4 significant figures, I could use 101.3 kilopascals as 1 atmosphere pressure. And that's also will support a column of mercury that's 760 millimeters tall. And 760 millimeters is 1 atmosphere. 101, that's also 101.3 kilopascals. So this gives me conversion from atmospheres, which is the unit you've probably seen before for pressure, into SI unit. Its SI equivalent is 101.3. 760 millimeters of millimeters of mercury is also a unit called a torr. It's named for Torricelli, the guy who invented the barometer. So these are some numbers that will come in handy. At first, I'll give them to you, especially the kilopascal one. I probably won't give you this one. You need to know that an atmosphere is 760 millimeters. Okay, now I want to show you an interesting calculation I did one time. I was just curious, so I started looking into it, and I looked up, and the average person, average size person, human adult, has about 2.2 square meters of skin. So there's a lot of skin, and some of us have a little more than others. I've got more than I want. But you know, when you total that up, 2 square meters times 101.3 kilopascal, that comes out to a compressive force of 50,000 pounds. Now think about it, ladies and gentlemen. You are being compressed at this moment by 50,000 pounds of force is pushing on every one of your cells. On your skin, it's compressing you inward. If you ever felt like the weight of the world is on you, well, guess what? It's not, but the weight of the atmosphere is. Now, I want to give you a little concept. Suppose I've got something pushing in on a cell, on your cell, with a pressure of 50,000 pounds. What's the obvious reason why you don't get crushed? okay? You've got to be generating an equivalent pressure inside. So you're generating enough pressure to hold those cells constant and keep them from being crushed into uh, non-existence. Well, so on the other hand, while you may have the weight of the world on you, hey, you the man, you got it. You can take care of it. You're built to take care of it and sustain that kind of pressure. Okay, well, let's look at now some of the laws that are related to the way gases behave. Boyle's law refers to systems that are held at constant temperature, and it says the volume of a confined gas is inversely proportional to the pressure. Now, you already know that. What's going to happen to a balloon if you squeeze it? It's going to get smaller, right? Pressure is going to go up inside there. So the volume and pressure are inversely related. If you apply a high pressure, it'll cause the gas to be compressed into a smaller volume. That's perfectly within our own experiences. We've seen that before. And so if pressure is inversely proportional to volume, it's some constant over volume, then P times V will be a constant. So let me take just a second over here. I want to show you this. So if I'm taking data in the lab and I make myself a graph of volume, like on the y-axis, against pressure on the x-axis, what you're going to get is a graph that mathematicians call a hyperbola. It'll look like that. When the pressure is small, the volume is high. When the pressure is high, the volume will be low. This would go only to zero when you get to infinite pressure, and this would go to zero at absolute zero pressure. That volume would go up to infinity as well and come out touching the line. So this is what it looks like. If you're taking data in the lab, you're going to get some scatter. And sometimes it's kind of hard to draw in the best fit line for that to verify Boyle's law holds. But now you can do a graph like this if instead of plotting volume on the y-axis, I plot the pressure times the volume on this axis and the pressure on this axis. Now, this will be a constant. So now if you've got data that's got scatter, it's pretty easy to draw a straight line through that data. Or, for example, you've been using Excel to do your graphings. So now the Excel could fit this to that form of a line if you give it that, and it'll give you the fit and R squared and all of that. But it works better and more visual to us if we have it plot PV times over P, and we'd get a straight line. Now that's going to be the point of the last experiment that we do next week. Be the last experiment for lab, is verifying various laws of pressure and volume and so forth. Boyle's and Charles and other laws will be the last lab that we do. So you're going to be looking for relationships like this, and whether if P versus V or V versus P is a line, or if it's not, you could try P times V against P and see if that's a straight line and do some stuff like that. So that's going to be, I think, the pre-lab of the last experiment. Okay, let's go back to screen share. Okay, now, so in Boyle's law, P times V will be a constant. It won't, it changes. If P goes up, V goes down, but the product stays the same. Charles' law is measured at constant pressure. And what Charles' law says, the volume of a confined gas is directly proportional to its absolute temperature, Kelvin temperature. And let me do this one over here because I want to make a what I think is a really neat observation. And what we're doing now is we're going to plot volume against temperature. And if the temperature is high, the volume is high. So we would be making some data points maybe like this, and this ought to be a straight line. So if you did this in Excel, you could get the regression line and you could get the intercept. The interesting thing is the intercept. So I take these data and I extrapolate, and it's much further back than this, but maybe out here is my data points that I'm doing in the lab. And, that's 25 Celsius and 30 and 35 and 40, numbers like that. Now, I want you to look at what this is implying. There is some temperature at which the volume of a real sample of gas goes to zero. Now, that's a contradiction. Way back in the beginning, I told you that matter had to have two characteristics. It has to have mass and volume. So here is a temperature at which the volume of a mass, say 5-gram sample of CO2 is zero. That's impossible. So that defines the lowest possible temperature, and we call that absolute zero. So if I do that on that scale, and I don't know, suppose there were my zero, it's not on volume, that's my origin. This distance back to here is minus 273.15 or 6 degrees Celsius. If you were to cool something down to that temperature, its volume should disappear. So that means it's not possible to reach that temperature, and that's really true. Let's think of the logistics of it. How do you get, if I told you, take the heat out of that pencil, how could you do that? You can't just look at it and say, heat, go away. What you have to do is you have to touch it with something colder than that. And that will cause this heat to flow from that warmer object to the colder one. And if you just keep them sticking together, the temperature of both of them would come down. The hot one would get colder, the colder one would get hotter, and you'd be able to cool this down. What if you're at absolute zero? How are you going to cool that down? That's right, there's nothing colder, no place for it to go. Now, I'm going to give you a logic question. What do you think? Suppose there was nothing in the universe colder than 25 degrees Celsius. What would the absolute zero be? You're right. It would be the coldest possible temperature. Would be, if there's nothing colder than 25 degrees in the universe, that's the coldest it could ever be. Is that zero? Well, no, it's just nothing colder than that. So when you get to absolute zero, you can't really say at absolute zero, there is no heat energy. You can't really say that. We don't know. All we do know is there's nothing colder than that to get any colder than what we call minus 273.15. So that is our absolute zero temperature. Now, you can't get colder than that, but we keep adding more digits on it. I told you I think it's 273.15. I think they've actually gotten down to maybe 4 or 5 other decimal places on that temperature. We can get closer and closer and closer and closer to it, but we can't get there. Now, there's some really interesting stuff that happens when you start cooling things down. If I take a wire and I wrap it in a coil and I pass a current through it, I can generate a magnetic field. from that. It's called an electromagnet. Now, if you take those coils and you start cooling them down, I'll give you an example in a minute. Say cool it down to 4 degrees above absolute zero. That's the boiling temperature of helium. So if you take helium and put something in it can cool something down to 4 degrees above absolute zero. So you could put that coil into liquid helium and get it down to 4 degrees above absolute zero. There are wires that when you cool them down that cold, you start a current flowing in them and it still continues to flow. And it creates a magnet that doesn't need power anymore. Now, an example of that is the nuclear magnetic resonance spectrometers I told you about that you'll be using in organic chemistry. We got those in while I was chair of the department. It's probably been, I guess we got them about 12, 15 years ago. When they brought the machine in and set it up, they put liquid helium in the space where the magnet, where the coil was located. The technician connected the wires to the power system in Murfreesboro, to the old science building, and the magnets came on, and the instrument was now ready to use. He took those, he unplugged it from the Murfreesboro system and attached the two ends to themselves, and the magnet is still running. It doesn't take any power at all. Now, when they first flicked it on, I imagine the lights all over Murfreesboro dimmed a bit because it's a very, very powerful magnet. And this superconducting magnet is still running. It's not plugged up to the power system, so if Murfreesboro's power system goes down, that machine is okay as far as the magnet is concerned. It's not going to do anything to it because the current's still flowing in that. When something becomes superconducting, it has a very unusual characteristic. A magnetic field cannot penetrate into a superconducting magnet's area. The reason for that is they will repel each other. And it is one of the most interesting things. If you want to Google it, there are videos out there. You can take a little cubical magnet that is a superconducting material, and you can put it near another magnet, either pole, north or south, and it'll float in the air. And it'll float over that magnet, and you can click it and flip it, and it'll just sit there and spin over that magnet and won't ever hit it. It'll float on top of it. And I thought, wouldn't it be cool if we could get superconductivity up to room temperature? You could pave the streets with magnets. I could have my driveway paved with a magnet, and then the street that I live on with magnets, and out on the interstate with a magnet, and all the way into the science building with magnets. I could push my car out of my garage. It would be floating on that magnet. I could just push it out of the garage, and I could do a Fred Flintstone all the way to Murfreesboro without any gas. Wouldn't that be cool? Or superconducting trains. We do have limited trains that run on superconducting magnets, but it has to have temperatures near. I think they've got them up to liquid nitrogen temperatures, minus 190 or something like that. But and we don't have to go all the way down to liquid helium. But there's an active area of research to try to find superconducting materials that become superconducting at temperatures that are easier to reach. It's fairly expensive to create any kind of superconducting material. But this is an experiment that you can do, and we used to do this in the lab. We would look at carbon dioxide and start cooling it down and heating it up and do a graph like this, and then estimate where absolute zero is in terms of Celsius. If we did this in Celsius degrees, we could find that intercept. And of course, it's really easy in Excel because all you do is tell it to give you the equation for the regression line, and it'll be y equals mx plus b. The m will be the slope, and the b will be the y-axis intercept, and it would give you an estimate of absolute zero. It's not perfect. You're not going to get 270 minus 273 in your lab, but you get the idea. It is a way of doing that, getting the measurement. But the Charles law is the ratio of volume to temperature would be a constant. So if I plot that like I'm showing here, or if I take V over T and plot that against T, I should get a straight line. And I could just draw my best straight line through that. So you don't get an advantage, I guess. This one's linear or that one's linear. But this one, if you're doing this, it gives us several ways of measuring this Kc constant, taking a ratio of volume to temperature in many different places like that. Avogadro's law says the volume of a gas at constant temperature and pressure is proportional to the number of moles. Now, doesn't that make sense? If I got 1 mole of gas in a container, I'll get a pressure. If I put 2 moles in the same container, I'll get twice the pressure. Or the volume, if I want the pressure to stay constant, the volume would have to double. And so this is another expression. V over N is a constant as well. So now this is Earle's hypothesis. And it's the pressure of a gas at constant volume and temperature is proportional to the number of moles. Well, we just said that a while ago. If you put twice as many moles into the same container, you're going to double the pressure.
Dr.
So,
Pierce, can you switch your camera?
Yeah. Oops, excuse me.
Mind switching your camera, Dr. Pearson? You're still on the paper.
I know. I'm coming right back to it now. Okay. Let's see. I need to go back. I need to escape out of that, and I need to go back to screen share. Okay. And let's see. I need to get back to where I was. Okay. So here are some relationships involving pressure, volume, and temperature. From Boyle's law, we see the pressure times volume is constant. From Charles' law, the volume over temperature is constant. From Avogadro's law, the volume over the number of moles is constant. And Earle's hypothesis is that pressure over moles is a constant. So the right-hand side of all of these are constants. So you could multiply them all together, and then you'd get something like this. And if I take the square root of both sides, I'll get P, V over N, and T is equal to some constant. And the product of these constants is R. So this is called the ideal gas equation. Pressure times volume is number of moles times R. This is a constant times temperature. The value of R we can very easily measure. I can put 1 mole of some gas in some volume in some container at 1 atmosphere pressure and at, let's say, if I did 273 degrees, if I do 0 degrees Celsius would be 273.15 Kelvin. If I do that at 0 degrees, which I can do with ice water and get that saved, I can measure the volume. The volume is 22.4 liters for 1 mole at 1 atmosphere and 0 degrees Kelvin. So you can solve for the value of R. The value of R is 0.08206, liter atmospheres per mole per Kelvin degree. So this is a constant that we have to use so often that you do need to memorize this number with its units. So R is 0.082. I usually just use 3 significant figures. If I wanted this other one, I would look it up. I don't usually keep that in my head, but it's 0.0821 liter atmospheres per mole per degree Kelvin to 3 significant figures. And that allows us to do a lot of calculations. For example, we can calculate the density of a gas. Excuse me. The density is mass over volume. So if I'm using the ideal gas equation and measure the density of a gas, it would be the pressure times the molar mass divided by R and T. You can derive that because N is the mass divided by molecular weight. So if I put that in up here for N in the ideal gas equation, then I'm going to have V over, or G over V. That's grams over volume is density. So the density calculates to be this just by plugging these numbers in and the definition of density. The density of a gas then is the pressure times the molar mass divided by R and T. The little takeaway from this is that the density is proportional to the mass of the gas, or in this case, the molecular weight of the gas. So air, for example, has a molecular weight of 29. So any gas that has a molar mass less than 29 will be less dense than air. It'll float up in the atmosphere. That's why helium, you put helium in a balloon and it causes it to float. It's because the density of the helium is less than the density of the air, so the helium is just going to float up in the atmosphere. If it's got a density greater than 29, then it will flow down in the atmosphere. I think I mentioned maybe one time before in passing that chlorine was used in World War I as a war gas. It's a terrible thing. It's been outlawed by the Geneva Convention ever since World War I. And what they would do is chlorine is diatomic, so its molecular weight is 71, 35 and a half times 2. So it's 71. So it's maybe 3 times as dense as air. So if they caught a group of their enemies down in a valley, they could just go up on the hill and release chlorine, and the chlorine would flow down just like water into the valley and fill up until it got to levels that would suffocate anybody in it. And in a big area like that, it's so fast acting that you can't get out of it. All you're going to do is just lay there and die. And it's a terrible death. Chlorine gas reacts with your moist lung tissue to make hydrochloric acid and just dissolves your lungs right out while you're living. It's a terrible, terrible thing. And they don't, it's totally illegal by every civilized group in the world would not use chlorine as a war gas anymore. But that's how to tell if something will sink or float. A more important, more likely one that could cause you trouble is carbon dioxide. Carbon dioxide has a molecular weight of 44. So, it's not quite twice as dense as air, but it's quite a bit denser than air, and it literally does flow just like water. And so if you've got a big forest, I'm thinking about the area around Mammoth Cave in Kentucky. If you've never been, it's kind of an interesting trip. But there's a great big opening for the cave. It's huge. It's called Mammoth. It's a huge cave, but it's in the area of a big forest area and so forth. And the leaves off the trees and all of that decaying debris forms carbon dioxide. Now, while the wind's blowing real good, it's not a big deal. It just dissipates. But typically at night, the winds die down and the carbon dioxide that forms flows, and it does flow into the cave. But it doesn't just sit there in the entrance. It flows down to the lower and lower regions of the caves. And Now they've got Mammoth Cave anywhere visitors are going to go. It's ventilated and has, um, fresh air brought in to keep the carbon dioxide from being a problem. But many earlier explorers that went into the very lowest regions of that cave never came out. And that's because the level down below had so much carbon dioxide in it, it would suffocate you. It's odorless, colorless, you don't see it or smell it. Um, you don't know it's there. You get lightheaded and you just fall asleep and don't wake up. So it'll suffocate you. So the density of a gas, we can tell whether it's going to float or sink in air just by comparing its molecular weight. Molecular weight of air is about 29. So that's kind of a number you could remember to tell whether a gas is going to sink or float in air. Now, now you can really measure the density of gases very well. And you can use this equation right here. And, this is one of my another one of my corny stories. Density, I remember that nights PM over the round table. I told you I got crazy ones. But anyhow, if you measure the density, you can get the molecular weight of a gas. That's really how we learned that oxygen was diatomic. Uh, they first tried to make oxygen, and as we get it here in air, just the weight of one atom of oxygen, 16. But when they did from relative weights, but when they did the density, they found it was diatomic because the mass turns out to be 32 instead of 16. And so this is a really historical, important way of getting molecular weights. You can weigh gases. It's a little bit tricky, but essentially, if you had a great big 1 liter bottle and you evacuate all the air out of it, and then you put it on your balance and weigh it, and then you attach it to, say, oxygen, open the little valve and let it fill up to 1 atmosphere with oxygen, and then close off the little valve and go weigh the bottle again, you would get the weight of 1 liter, and you could convert that then to density, and you could calculate the molecular weight of oxygen or whatever gas you put in the bottle. So you can do that. It's a fairly simple experiment. Now it turns out with gases, you do have to worry about one little problem. If you're weighing it in air, remember air has a mass as well. So when you put that bottle out into air, it's pushing its own volume of air out. So if you want to get accurate measurements, you have to add that mass of the air you pushed out by setting it on the balance. You have to add that weight back in order to get the actual density of the gas inside and get it more accurately. But this is not a difficult thing to do. Excuse me. Now, remember now, volume is proportional to gas, to number of moles. We just saw that a while ago. That was Avogadro's law. Well, Gay-Lussac looked at that and thought, okay, the volume of gases that react with each other should be in the ratio of their balancing coefficients, small whole numbers. And so from that, Avogadro then said that would imply then that equal volumes of all gases at the same temperature and pressure are going to have the same number of molecules. And that's why the law of combining volumes work. And that makes the calculations really, really easy. Let's jump over here for just a minute. Suppose I have a reaction of nitrogen and hydrogen to make ammonia. Balancing would be 2 and a 3 and a 1, I think. Okay? what the Gay-Lussac law says, that if I took 1 liter of nitrogen at 25 degrees and 1 atmosphere pressure, it would need 3 liters of hydrogen at 25 degrees and 1 atmosphere pressure to completely react, and I would get 2 liters of ammonia when the reaction is over. So you can use these balancing coefficients then just like volumes. So and this is another case of gas stoichiometry, that we have our little magical scoop. It's a volume liter, 1 liter of nitrogen, 1 scoop, and 3 scoops of hydrogen would make 2 scoops of ammonia. So this is a case where we can use volumes as we are doing chemical reactions. In gases, that makes the chemistry really easy. We just take a volume in the same ratio as the balancing coefficients when we carry out the reactions. Here's one with hydrogen and oxygen to make gaseous water now. Water is liquid at room temperature, but if we do it in the gases, say certainly over 100 degrees Celsius, H2O would be a gas. So you'd need 2 liters of hydrogen and 1 liter of oxygen. It would make 2 liters of water vapor. Now, let's just ask an obvious question. What happens to the volume if I take a container and I put 2 liters of hydrogen and 1 liter of oxygen in it, and then I cause this reaction to take place? What would be the volume after it's done? Yeah, it would be 2 liters. So the volume would change during the chemical reaction. And that would just be a part of the reaction that would take place. There would be a volume change that would take place because the gases, equal volumes, always occupy the same volume. I mean, equal numbers of moles always occupy the same volume. Okay? So if you take these reactions, this is what you're going to get. Let's do a couple of reactions, a couple of problems. The idea here is to just do some working with that Pascal unit and the MKS system. It's probably unfamiliar. Okay. Let's say a pencil has a mass of 5 grams. That would be pretty close. I like to do things to help you visualize and get things in your head about how much a gram is. A good rule of thumb, it's very, very accurate. A nickel weighs 5 grams. Okay? That's easy to remember. So if you know what a nickel is like, you have an idea how much 5 grams is. A gram would be 1/5 of the weight of a nickel. Now, so this is about the weight of a pencil. And now it's standing on the point. If the point has a radius of 1/10 of a millimeter, which would be decently sharp pencil, calculate the pressure the pencil would exert on the table in pascals. So let's remember what pressure is. Pressure is force per unit area, and a pascal is 1 Newton per square meter. Gravitational force on a pencil is the mass times the gravitational constant, and that's 5 grams. That's 5 times 10 to the negative 3 kilograms. And we've got to multiply that by the acceleration constant on Earth. The average is to 9.807. And so if I multiply 5 times 10 to the minus 3 times the G, gravitational constant, I get 4.904 times 10 to the negative 2 newtons. So that is the force then that is being exerted on this little area that the pencil is resting on. Now the area is pi r squared. The pi is 3.142 and r is 0.1 millimeters. So I'm going ahead and do it in millimeters first. So that squared will be in millimeters squared. Now I'm going to convert from millimeters to meters. So there's 1,000 millimeters in 1 meter. So 1,000 squared. So do my math. That comes out to be 3.142 times 10 to the negative 8 meters squared. Okay, so the pressure is going to be that many newtons, we calculate up here, divided by that many meters squared. And it's 1.56 times 10 to the 6 pascals. That's 229 pounds per square inch. So that's a pretty hefty pressure that pencil is exerting if it's just standing upright on the point. Now, it should be pretty obvious that it should be easy to explain my observation. Every time I drop a wood pencil, I can guarantee you it'll break the point. Well, there's why. It's going to be hitting with a force in addition to what it would have just standing still. And that's just standing up on the point would be 229 pounds per square inch. So that's still quite a bit of pressure. 9.63 gram sample of carbon dioxide is trapped in a piston that initially has a volume of 3.5 liters when the pressure is 155 kilopascals and the temperature is 25 degrees Celsius. So I've given them I've given the mass, I've given the volume, I've given the pressure, I've given the temperature. What force must be exerted on the piston if the area is 100 square centimeters in order to reduce the volume from 1 liter if the temperature to 1 liter if the temperature doesn't change? So I'm going to change the volume from 3.5 liters down to 1 liter. So I'm going to have to increase the pressure on that to do that. Okay, what would I need? Well, this is the relationship for Boyle's law. Pressure times volume is a constant. So the initial pressure times the initial volume equals the final pressure times the final volume. The final pressure is 155 kilopascals. This is the pressure of one of them. And so I'm solving, this is the initial pressure. This is the ratio of the volumes. So the pressure at the lower volume would have to be 542.5 kilopascals. So the pressure would have to go from 155 kilopascals to 542.5 kilopascals in order to affect a volume change from 3.5 liters down to 1 liter. Now, always think of your logic here. This pressure is going times this volume has to equal this pressure times this volume. So if I want the volume to go down, the pressure has to go up. So my answer here should be larger than the initial pressure. And that's what we've done here. And so that data looks okay. Now, pressure is force over area. So let's put in what we know. And the area, we've got the area of the piston, it's 100 square centimeters. And we've got to convert that to meters. So that's 0.01 square meters. So the force is the force we calculated up here, 542.5 kilopascals. So I've changed from kilopascals now to Pascal is now newtons per square meter. And there is my area. So I can calculate the force that's going to be required. It's going to be 5.43 times 10 to the third newtons, or 5.43 kilonewtons, if I wanted to do everything. What temperature would the sample in number 2 be cooled to affect the same volume change if the pressure is held constant? So this is Charles' law, and it says V1 over T1 has to equal V2 over T2. So I've got my volumes and my temperatures, and I can solve for the new temperature. And do the math, I get 85.2 degrees Kelvin. So I would have to cool this gas down to 85.2 kelvins in order to reduce the volume from 1 liter down to 3.5 liters down to 1 liter. That's minus 188 degrees Celsius. That's really not quite possible because we're dealing with CO2. It freezes solid at minus 56. So I wanted to use this to illustrate a point. This is the ideal value. This is what you would expect to happen. CO2 is not really an ideal gas. It doesn't behave by Boyle's and Charles' law like it should. And it's certainly not at this temperature range. It's going to look really, really bad because it's going to be below its freezing point. CO2 is called dry ice. And the reason why it's called dry ice, it looks like ice when you see it, but it gives off carbon dioxide. It's solid carbon dioxide, and it goes directly from the solid phase into the gas phase without ever melting. That's a process called sublimation. There are some things that will sublime like that. Most anything will at some set of temperature and pressure conditions. And that's the way we purify a lot of stuff, is we take the crystal and our mixed crystals with impurities in them, and we can put them in a particular chamber. And if things are just right, we can heat it up to some temperature where the solid sublimes. If we put something cold at the top, then those pure vapors will come up and condense on that cold spot, and we can collect the pure crystals. That's how we purify stuff sometimes. You'll do that in organic chemistry. It's called sublimation. When you carry out a reaction, often you get mud. And what you want is a pretty yellow crystal. And you have to figure out ways to get those pretty yellow crystals out of the mud that came out of your reaction. And sublimation is one of the ones that you could use. That's usually done at the last stage of purification because that's one of the most effective ones if you've got it almost pure already. All right, so this is not going to happen in real life. Now here's a combined gas law problem. And if you put rearrange the gas law like that, it would be equal to R, the constant. So P2, V2 over N2 and T2, this now allows you to vary pressure. It allows you to vary volume, and vary number of moles, and vary temperatures. What do we got? 8 things in there. You can put values in for any 7 of them, anything you want, and calculate the 8. So this gives the relationship between all of them. If number of moles and temperature is constant, you get Boyle's law. If pressure and number of moles is constant, you get Charles' law. If you have volume and temperature constant, you get Earl's law. All right, so I can plug in the data from the problem. These are my initial temperatures, 155 kilopascals, 0.219 moles, and 298 degrees Kelvin. These are the final temperatures that final pressure, final number of moles and temperature. Volume is held constant, so I can plug in my data and solve for the number of moles that I would need in the container to do that. So I need 0.373, and we started out with 0.219, so I'd have to add that difference, 0.154 moles of the container of gas into the container to make the pressure drop from 3.5 down to 1. So that's about 6.78 grams of carbon dioxide I'd have to add in order to make that happen. Now, what mass of carbon dioxide in a balloon has a volume of 10.5 liters when the temperature is 25 degrees and the pressure is 1 atmosphere? So we've got the volume given, we've got the temperature, we've got the pressure. So we can use the ideal gas equation to solve for that. Find the number of moles. I've got 1.35 atmospheres pressure. Volume is 10.5 liters. The ideal gas constant is 0.0821, and the temperature for 25 degrees is 298 Kelvin. Add 273.15 to that. to 225. And we can solve for the number of moles, 0.579 moles of CO2. That's how much you would have to have. It would be about 25.5 grams. What's the density in grams per liter of nitrogen gas at 1.25 atmospheres and 35 degrees, 35 degrees Celsius? Okay, it's got ideal gas problem. PV equals nRT, and there's number of moles over volume is going to be P over RT. So the number of moles is G over M. So again, G over V is equal to P times M over RT. The knights over the round table. All right, so the density, I can just plug the numbers in. 1.25, 28.5, 0.0821, 308 is the 273 plus 25 is 308 kelvins. And we plug in, we get 1.38 grams per liter. Now, I wanted to do the exercise, but I wanted to give you an idea. If you're dealing with most gases, the density of most gases is going to be somewhere between 1 and 10 grams per liter for the common gases. So it's in, the units are going to be in grams per liter. And you're going to get something like 1 to 10. So if you're calculating a density of some reasonable gas, and you get a density of, oh, I don't know, 48.4. No, that's probably not right. You made a mistake. Or I get a density of 0.0724. That's probably wrong too. There's nothing going to be less dense than hydrogen, H2. And if you can very easily calculate the density of any gas you want to. I'll let you do this one as an exercise just to see what the density of the heaviest gas that I know about is uranium hexafluoride. It's a gas at room temperature, and this is the way at Oak Ridge, Tennessee here, they was able to separate the isotopes of uranium and get out the uranium-235 that is used for making bombs. Ordinary uranium can't make an atomic bomb. You can't use the 238 isotope. You have to use the 235 isotope, because when the 235 isotope of uranium absorbs a neutron, it becomes uranium-236. Uranium-236 is completely, absolutely unstable. And it's so violently unstable that the uranium-236 atom, our isotope that's formed, immediately breaks apart into at least two big pieces. And those two big pieces have considerably less mass than the uranium-236 isotope had. That mass gets converted into energy by E equals mc squared. So you take the speed of light and square it. That's about 9 times 10 to the 16th, or roughly 10 to the 17th. So that mass that's lost times 10 to the 17th is an awful lot of joules to happen in a nanosecond. And that is a tremendous explosion. That's the atomic bomb explosion, comes from that. So you can calculate what the density of uranium hexafluoride is. Just put the number in there for its molecular weight and do this same calculation and see what you get. Now you're going to get something probably greater than 10, but it's going to be a reasonable number. And that'll be kind of an upper limit, at least of the gases I know about. There may be some others, but I can't think of anything right off the top of my head that's gaseous at room temperature that has a molar mass bigger than uranium hexafluoride. All right, now let's do some more problems with it. We've got a reaction of ammonia and NO2 to make nitrogen and water vapor. And let's do the calculation. I've got 3 liters of ammonia and 5 liters of nitrogen dioxide. I pass it over a catalyst at 500 degrees. That's just to make it happen. And the pressure is 2.5 atmospheres. What volume of product gases dinitrogen and water vapor will form at this temperature and pressure. I've got two amounts given. That's a limiting reagent problem. So the amount of ammonia is 3 moles. I put that over there. The amount shown in the equation is 8, or 3 liters and 8 liters. And divide them out, I get 0.375. That's the rebalancing factor based on ammonia. I put 5 liters of NO2, 5 over 6, and that gives me 0.833. The limiting reagent then is the ammonia, 0.38. So I'm going to take that and multiply by 7 liters. That gives me the nitrogen value. And times 12 would give me the water vapor value. So the total value of volume of the products would be 0.375 times 7 plus 12 would be 7.125 liters. What volume of nitrogen dioxide will be formed at 745 torr and 35 degrees by the reaction of 1.5 grams of copper with 10 milliliters of 6 molar nitric acid. This is the balanced equation for that reaction. And again, we've got a limiting reagent problem. We're dealing with copper and nitric acid and nitrogen monoxide as in this particular problem. And now for the copper, I've got 1.5 grams of copper. The equation is showing 3 moles, and that would be 3 times 63.55. So my rebalancing factor for copper is going to be this number. Now, if I take 10 milliliters of 6 molar, I get 60 millimoles, divide that by 8,000 millimoles. Or if you did the way I did the last time, write that not 10 milliliters, but 10 times 10 to the minus 3 liters times volume, then I could put this in moles, and this denominator would be an 8. It'd be the same problem. Okay, here are my two numbers, 0.0787 and 0.00750. This is the limiting reagent because that rebalancing factor is smaller. So I can calculate then the number of moles that I'm going to get for the NO. So I've got this many moles. The problem wanted to know the volume at some temperature and pressure. So I have to now use the ideal gas equation and solve for the volume. There's the number of moles. There's the R constant. There's the temperature in kelvins. There's the pressure in atmospheres. So I calculate 0.387 liters. Now, remember, when I get all of this stuff plugged in and do the math on the calculator, 0.387 is what's showing on my screen. I have to know I calculated a volume. In the MKS system, volume is liters. So this is going to be in liters. And I've put my R is liter atmospheres. So there's where the unit comes if you cancel all units out and make it work that way. Okay. But I know the answer ought to be in liters anyhow because I'm calculating volume in the MKS system. So if I wanted the answers in milliliters, then I just need to convert that to milliliters. Remember, milli is 10 to the negative 3. So 387 times 10 minus 3 would be equal to that number. Okay, here's some checkpoints on this. And I think after this, we're going to take a little break. Right. And we're all set up. So here's the problem. It says the latex balloon has an inflated volume of 5 liters. What mass of helium is required to fill the balloon at 25 degrees in 1 atmosphere? And then what mass of air, average molecular weight is 29, would it take to fill the same balloon to the same volume at the same temperature and pressure? And it says this is an easy problem, so there's probably an easier way to do it than the first thing you think of. The difference in mass of the balloon is how much the balloon could lift. See, if I take the the mass of the air in the balloon and the mass of the helium in the balloon, then that's the difference in mass. That's how much the balloon could lift if the balloon had no mass. If the balloon has a weight of its own, then we have to subtract that from that difference, and then that difference is the one that gives me the lift of the balloon. Okay, and then here's another problem. So let's take this off and put that where I can see it. Okay, now the number one was the balloon has a volume is 5.0 liters. What mass of helium? To fill the balloon at 25 degrees C and 1 atmosphere pressure. Well, now that's going to be an ideal gas problem. PV equals nRT. So I wanted to know the mass, so I'm going to have to know the number of moles first. So the number of moles I'm going to get is P times V over R and T. Now, the pressure is 1 atmosphere. Okay, that's good. The volume is 5 liters. R is 0.0821. And the temperature, always remember, that has to be in Kelvin. So it's going to be 25 plus 273. All right, so let's do our math and see what we got. Need to do the math with a calculator. And so we have 5 divided by 0.0821 and divided by left 25 plus 273 right. And that's, if I haven't made a mistake with my math, and it looks like it's set up correctly, I get the number of moles as 0.204. And there's a whole bunch of digits, 3, 6, 6, 9, 1, 2, 2. And I did that to just emphasize I haven't rounded off anything yet. I don't want to. But it set the mass. Now, the mass divided by the molecular weight would be the number of moles. So that's going to be 0.204 and all those digits. So the mass is going to be all of those digits times the molecular weight. And this is helium. And helium is 4.0 watt. Let's see. Helium. Four 4.0026 or something. Okay, all right. 4.00. Let's say. So all I got to do is take my answer I've got on my screen and multiply it by 4. And I get 0.81764678.7. And it looks like I have 3 significant figures everywhere. I should put another decimal point on that, but it wouldn't really matter. It'd still give me at least 3 significant figures. So I think I'm good to 3 significant figures. So 0.817 would be the mass. The second part was, what is the mass of air that it would take to fill the same balloon to the same, so the mass of air that it would take. Well, that's just, it told you the molecular weight is equal to 29. Now, Um, the molecular weight is 29, and I could go back through this whole calculation. Everything is still the same to here. I get this 0.204 moles, and I'd multiply by the molecular weight of air would be 29, wouldn't it? Okay. So I could do the math like that. I said it was an easy problem because this is the mass of helium, and I'm trying to get the mass of air. The difference is the two molecular weights. So all I got to do really is take my answer here, 0.817, and multiply it by 29 divided by 4. That's why I said it was an easy problem. That's the molecular weight of air, and that's the molecular weight of helium. So the mass is going to increase in the same proportion. So if we did that, that'll get the quick answer. So I've got that number there on my screen. So if I multiply that by 29 and divide it by 4, that gives me 5.93 to 3 significant figures. So that's how many grams of air that it would take. And now the difference between those two, so the lift would be 5.93 minus 0.817 would be the lift. So if I take that number minus 0.81746, a bunch of digits like that, I get the lift would be a little over 5 grams, 5.10 grams. So that would be the lift. If I really wanted to make this a practical problem, and say the balloon weighed 2 grams. If the balloon weighs 2 grams, I just made this up, 2 grams, then the lift would be 3.1 grams. So I could, that was, I told you masses of things, nickel weighs 5 grams. Turns out that a penny weighs 3 grams. So I could keep that balloon from floating up in the air if I put a weight on it greater than 3.1 grams. If I put a penny on it, it'll probably float slowly up into the atmosphere. Okay. All right. Isn't that fun? I think it is, really. I'm always intrigued by things like that. By things like, why is it that clouds form up there in the sky, not down here on the ground? Well, that must mean the water vapor floats up, doesn't it? Should it? Molecular weight of water vapor is 18. Molecular weight of air is 29. So sure enough, water vapor floats up. Now, if you're a practical thing, you wash your dishes, and let's say you wash them in really hot water, you wash a glass. What does most people do when they get to wash the glass washed? They set it upside down on the drying table or drying cloth or whatever. No, that's okay while there's liquid droplets in there, because the liquid droplets will run down and go on the table or on the drying cloth. But the water vapor that's in it will float to the top. Next morning when you come in there, it's still going to have water in the top of it. What do you do? Wash them in hot water, put them over on the drying cloth, or shake them out a little bit to shake all the water out, and then turn them right side up. You come back the next day, and that will be totally dry inside. You put a spoon on the drying cloth. Most people will turn it down. Well, that's good while there's water vapor in the spoon. But If you want it to dry properly, just spin air, then shake the water off, turn it right side up, and set it on the drying cloth. And then in an hour or so, it'll be perfectly dry with no water vapor still in the top of the spoon when you came in the next morning. I mean, all these practical things. Why are clouds flat on the bottom? Because they're setting on something. What are they setting on? Inversion layer. They're setting on a layer of air that is denser than the cloud. So the water vapor floated up through that inversion layer, condensed into clouds. That massive little water droplets in the cloud started to sink into the atmosphere till they came to that inversion layer, and they're sitting on the inversion layer. That's a little sphere. From us down here, it looks like a flat. See, chemistry is fun. Okay, all right, the next problem. Suppose 6 grams of ammonia and 6 liters of NO2 are reacted to completion. What volume of N2 will form if the reaction is carried out at 740 torr and 37 Celsius? So my chemical reaction is 8 NH3s and 6 NO2s goes to 7 N2 and 12 H2O. And I did put the state subscripts on them, but they're all gases, so we'll just make sure that we did notice that. We're going to put in 6 grams of ammonia and 6 liters of NO2 at 740. Pressure is 740, temperature is 37 degrees Celsius. Now, it would be tempting to say, okay, my rebalancing factor here is 6, and this is in grams, so it's 8 moles. Molecular weight of ammonia is about 17, 14 plus 3 hydrogens. So that would be a rebalancing factor on that one. Now, that would be okay. But we're telling mass here and volume here. You can't do that. You can't compare these unless they're in the appropriate unit corresponding to the other one. So there would be 2 ways to work this problem. If you wanted to work this problem as a law of combining volumes problem, then what you would do is take the 6 grams, and let's do that. Let's convert 6 grams to its equivalent volume at that temperature and pressure. Then I can use those relationships. So I'm not going to do it that way this time. I could keep this and change this to grams or moles, and then I could do this. I'd change this to moles, really. But anyhow, over here. So I've got PV equals nRT, and I want the volume. Volume is number of moles. It's 6 grams, and the molecular weight is 17. That's the number of moles. R is 0.0821. The temperature is 37 plus 273, and divided by the pressure, and the pressure is 740 over 760 atmospheres. Okay, so now I've got all my units right. So let's just do the math. I know if I've got a number in the denominator of the denominator of the denominator goes to the numerator. So that'll make my math a little easier. I could do it that way, but this makes it simpler. So I've got 6 divided by 17. Then I want to multiply by 0.0821. Then I want to multiply by left 37 plus 273, right? Then I want to multiply by 760, and I want to divide by 740. So if I haven't screwed up somewhere, I come up with 9.22 liters. At 6 grams would be 9.22 liters at 37 degrees and 740. So I go back to my problem now, NH3 and 8 NH3s and 6 NO2s goes to 7 N2s and 12 H2O. I'm just dealing with these three. Okay, now I plug my numbers in. 9.22 liters of this at that temperature and pressure. This would be 8 liters. This is 6 liters, and this is 6 liters. So my rebalancing factor here is 9.22 divided by 8. That's 1.1525. 6 divided by 6 is 1.00. So this is my limiting reagent. That makes it cool, you see, because if this is a limiting reagent, then I can just take this coefficient is a 6, my rebalancing factor is a 1, the answer is going to be 7. 6 liters of this reacts with 7 liters, forms 7 liters of that. So I'm going to get 7 liters of N2 in the reaction. And if I chose the other way, then what I would have done is I would convert this 6 liters of this into moles, and then I'd take however many moles of this I had and divide it by 6. That gets me the rebalancing factor here, and the rebalancing factor here would have been less than what I got when I took 6 divided by 8 divided by 17. I would get this still to be the limiting reagent, and that would be 7 liters then, if I'm doing it in terms of moles or whatever. Take that factor, still going to be the same. Okay, so this particular problem had a couple of ways of working it. As I recall, a lot of people just got caught up in using using the rebalancing factor here in terms of grams, but the rebalancing factor over here in terms of liters, and that won't work. It will in moles, but it won't in liters. You have to use the ideal gas equation to convert one to the other. It doesn't matter which. You can take 6 grams, as I did, and convert it to 9.22 liters. Take 9.22 divided by 8 to get your rebalancing factor. And then 6 liters divided by 6 gives you this rebalancing factor. You can do it that way. You can take the 6 liters, calculate the number of moles it turns out to be, take that number of moles and divide by 6, and take this and divide out, and you would come out, it'll turn out in this case that you'll still get this 1 as a rebalancing factor over here. When you do that, that'll come out to be 6 liters, I think, when we do it. Okay, all right, I think that's it. And I think this would be a good time to take a little bit of a break, and maybe 5 minutes or so, and then we'll come back and finish up. And if we have any remaining time, we'll go over the practice quiz with you. Okay, I'll see you in 5. Okay. And here we are. And we're dealing now with some of the other relationships that follow from the ideal gas equation. One is the Dalton's law of partial pressures. And it just says that the total pressure of all the gases in a mixture is the sum of the pressures each one would have if it were by itself in the container. Those pressures we call partial pressures. So the partial pressure of air, of the gases in air, would be the pressure of nitrogen and the pressure of oxygen in the air. And 4/5 of the air's molecules are nitrogen and 1/5 are oxygen. So what would you think, what would you expect the pressure of each one of them to be if the atmosphere pressure was 1 atmosphere? Well, you'd expect 4/5 of that atmosphere would be nitrogen and 1/5 would be oxygen. So that is what happens, and it follows from these relationships. So now, where we make use of Dalton's law of partial pressures in the laboratory is the way we always collect a gas in the laboratory is generally by water displacement. What you do is you fill a bottle full of water and turn it upside down and put it inside another container full of water, and so that there's no bubbles up in the bottle. And then the bottle opening is down at the bottom. So you put a little tube down there that generates the gas that you want. Like, I don't know, maybe you're making hydrogen. Take zinc and hydrochloric acid and react them together and produce hydrogen. And then you take the little tube from your chamber where you're generating the hydrogen, put it under the bottle, and it will bubble hydrogen bubbles up into the bottle, and you'll displace the water. The water will come out and the bubbles will go in, and you'll fill the bottle full of hydrogen. And then you can do experiments with it or whatever. Or if you're making oxygen, we do that sometimes. We generate oxygen in the lab by heating potassium chlorate. And if you heat the potassium chlorate to about when it melts, it decomposes, makes potassium chloride and oxygen. And that's the laboratory preparation of pure oxygen. And then you can bubble the oxygen into a water-filled bottle. And then once you get it full, you put a glass plate over it and set it back out on the bench. You can turn it right side up now and set it back out on the bench with a glass plate over it. And then you've got a bottle full of oxygen. Well, the bottle isn't just full of oxygen. It's oxygen and water vapor. So the total pressure in the air is 1 atmosphere. You can look up in the back of the book and see what the vapor pressure of water is at the lab temperature. And that would be the pressure of the water in the container. So if I take the atmosphere pressure, subtract off the water pressure at that temperature, I've got the pressure of the oxygen that was in my container. So we make use of this, and it just makes logical sense that the total pressure is the sum of the partial pressures. So if I put so many moles, some amount of one gas, oxygen, some amount of another gas, water vapor, the sum of those pressures will be equal to the total pressure in the lab room. And we make use of that. Now, if the gases are ideal, we can calculate the partial pressures. It's the number of moles times RT over V. So I can take any one of these. I could calculate what its partial pressure would be, and I could add them all up. Now, related to this is what's called Raoult's law, and what I inferred a moment ago when I was talking about the pressures of the molecules in the air. The pressure is proportional to the number of moles. So the pressure of each gas is proportional to its number of moles, but the total pressure is also proportional to its number of moles. So the pressure of a particular gas is just the mole fraction of that gas times the total pressure. So like I said, if the atmospheric pressure is 760 torr, 1/5 of the air is oxygen and 4/5 is nitrogen. So 1/5 times 760 would be the partial pressure of oxygen, and 4/5 times 760 would be the partial pressure of nitrogen in the atmosphere. So this is called Raoult's law. And I mean, this is a mathematical equation, but just logically, doesn't it make sense? The pressure of a gas is proportional to the fraction of the total that is that gas. So that's a very useful relationship. Now, if you look at this side and solve for it, the mole fraction of a gas in a mixture is the partial pressure of that gas divided by the total pressure. Now, that would be pretty easy to do, really. Think about it. I take my container and I put my oxygen in it and I measure the pressure. And now I just take the lid off, let it fill with air. That will be the pressure of the air. If I take the first pressure with just the oxygen in there, divided by the pressure with everything in there, I'll get the mole fraction of oxygen in that mixture. And that we're going to use in Gen Chem 2 as a way of getting molecular weights. Mole fraction is the moles of gas I divided by the total number of moles present. It's called the mole fraction. It's another way of doing concentrations. So the pressure of the gas is proportional to the mole fraction. This works in a solution as well, because some of the things we dissolve are volatile. So if I wanted to know what the pressure of, say, alcohol would be in a mixture of alcohol and water, well, if I just take the mole fraction of the alcohol in the liquid solution and multiply by the pressure that alcohol has at that temperature, that will give me the pressure that would be over a mixture of that alcohol and water. This is a very useful relationship as well. There's a checkpoint on this. I think I'm just going to let you work on these. These are fairly simple. And I looked ahead a while ago. We've got a ways to go, and I want to be sure to get everything in. So I won't do the checkpoint problems unless we see there's going to be enough time to get everything in. Okay, now what I want to look at now is how can you explain the properties of gases? Now, we know they're compressible over great distances. We know the gases diffuse to fill their entire container. So we've got an idea of what gases really, how they really behave. Now I want to see if I can understand that behavior, focusing on the molecular properties that must be present in that gas for that to be true. One of the characteristics, one of the things that we believe about gases is that the particles of gases are very tiny particles and they're in continuous random motion, that they're moving fairly fast. Just as a rough estimate, the velocity of the molecules of air are in the order of a few hundred miles an hour. So they're moving around pretty fast in air. And we think those molecules are really, really tiny. Well, I don't see any. So they're very, very tiny particles. We think they're in continuous random motion because well, take ammonia. Ammonia stinks. And if I take a bottle of ammonia and I uncork it, and pretty soon, if I'm holding the container, I'm going to smell it first. But pretty soon, everybody around me is going to smell it. And the reason why we can smell it is that the molecules that are in the bottle are moving in every direction possible. So some of them are moving toward the hole at the top, the neck of the bottle and out the opening. And so they get out. Well, they would come right straight out of that opening, but I'm holding it out here a few feet in front of me, but I smell it. How did it happen? Well, those molecules came out and hit other molecules of air. When they hit the other molecules of air, they bounced off in random directions, and some of them bounced toward my nose and eventually got there. And they actually get there pretty fast. So the fact that we are able to notice molecules completely filling the container they're in and escaping through even the tiniest orifice in the container, then we believe we got a lot of particles in very fast, continuous, and random motion. And I've already told you the randomness in the motion is what causes the temperature. The more random the motion, the higher the temperature. Or conversely, the higher the temperature, the more random the motion of the molecules. So since diffusion occurs in every direction, we believe this is evidence that gases are like that they're made of large numbers of very small molecules or particles, moving in random directions. Now, we also believe that the total volume of molecules in a container is insignificant compared to the volume of the container. How would I think that? Well, gases are extremely compressible. So I can compress them down, and if there is a limit, it would be the point at which the molecules are all touching each other. Once the molecules are pressed to the point, compressed to the point that the particles are touching each other, then I couldn't compress them anymore. But in reality, I can go over thousands of I can take the volume of the container and reduce it to 1,000th of its original volume, and the gas is still in there and still behaving like a gas. So we believe that most of the container is just empty. And if I were to put all the molecules that are there in a little layer at the bottom of the container, the volume of that little layer at the bottom wouldn't be measurable compared to the volume of the container itself. And we get that idea then because gases are observed to be extremely compressible over great volume changes. Now, we believe there's no forces between particles of gases. Now, why would that be? Well, let's suppose two molecules attracted each other, but on the average, they're far enough apart that the attraction is small. Well, if I start compressing that molecule and getting those compressing that container and getting those molecules closer and closer together, eventually I could get them close enough that the attraction would take over and they would suddenly all come to liquid. Well, that's not something that we normally see in particles. And if they had no force between them, I could keep pushing them all the way until they touched, and it would still be, we'd still have Boyle's law obeyed. So that is what we observe. We don't really observe gases liquefying after we put a little pressure on them. Now they can at some temperature, but normally that's not the behavior we see or expect. But if there were forces between the particles, that is what would happen. Since that's not what we see, we believe that, and as long as Boyle's law is holding, we believe there's no forces, no significant forces between the particles, either attractive or repulsive. Otherwise, Boyle's law wouldn't hold. Now, here's one that's maybe not so easy to judge, but you can do the experiment that shows that this has to be true. Now, we believe that the collisions between molecules and with the walls are elastic. That means they bounce off with just as much energy after the collision as they had before the collision. Well, let's take the converse. Suppose that weren't true. Every time two molecules hit each other, they would lose a little bit of their random kinetic energy. And so when they hit the next time, they'd lose a little more. And the next time they'd lose a little more. So if they lost energy on all the collisions, now to put this in perspective, the molecules of air are bumping into each other about 10 to the 16th of them per second. So they're bumping into each other pretty quickly and pretty often. If every one of those 10 to the 16th collisions resulted in a loss of just a little bit of energy, what would happen? Well, you just see the gas setting there, and all of a sudden there would be liquid where it used to be, because they'd keep losing energy until they were no longer gaseous. So this doesn't happen. We don't see that happen. And the only way that could not happen is that the collisions are reasonably elastic. You don't do spontaneous, gases don't spontaneously convert to liquid at constant temperature and pressure. And this one is also something that maybe as we can observe and prove that it's true, but maybe we don't know that. But it is true that the average kinetic energy of molecules of a sample of gas is directly proportional to the absolute temperature. So as we raise the temperature, we raise the randomness in the motion. That's true. But at the same time, the molecules speed up. And they speed up in so that if I double the absolute temperature, I would double the average kinetic energy of that sample of gaseous molecules. Now, this is true for gases. What the books don't tell you is this is really true for everything: liquids, gases, and solids. The only difference between them that really makes any appreciable sense or significance is the distance they move. In gases, molecules move great distances. Compared to their molecular diameters, maybe they move 1,000 or 50,000 diameters before they encounter another molecule. Remember, the volume of the container is mostly empty space. So they move long distances before they bump into each other in gases. And all of the time they're moving, they have a kinetic energy, 1/2 mv squared. It's the definition of kinetic energy. So they have a kinetic energy as they're moving through the gaseous space. Now, suppose you have the same substance or any substance at the same temperature in a liquid. Well, what happens on a molecular level in liquids? Well, you can imagine around the liquid molecules, there's a cavity, and an individual molecule is bouncing around within its own little cavity, sort of like one molecule in a bottle. Well, there's a cavity around each molecule in the liquid, and there's a molecule inside that cavity, and it's bouncing around. The cavity is formed by the other molecules around it in the liquid. So the molecule is bouncing around in that cavity. It's going from one end to the other, bouncing around like that. And as it does that, it has an average kinetic energy. And inside that cavity, it's just like any other gas. So the average kinetic energy of molecules in a liquid is still going to be 3/2 RT is what it turns out to be. It's equal, its kinetic energy is proportional to its absolute temperature. Now, the difference between a liquid and a solid is they both are in cavities. But in the liquid, the cavity moves. In the liquid, the individual molecules, it can move into one of the cavities around it, and we get that molecule diffusing through the liquid, but it's still inside a cavity, and it's still behaving like a gas inside the cavity. So its average kinetic energy is proportional to its temperature. 3/2 R times T is its average kinetic energy. If I've got a solid, the only difference between the liquid and the solid is the cavities don't move. In the solid, the particle that's inside the cavity is bouncing around inside the cavity, and the cavity is formed by the adjacent atoms or molecules or ions that are also in the solid state. But each particle is bouncing around within its own cavity, but the cavity never moves. If I were to think about a salt crystal, a nice cube of sodium chloride, if I could paint let's suppose I could paint that very corner tip molecule blue. I could come back 1,000 years from now, and that blue molecule, that blue ion that's in that corner, that cavity in the corner would still be there. It would never move out of that cavity. So whether it's a molecule or an ion or whatever, it's not going to move outside of its cavity in the solid state. But within its cavity, it's still moving with an average kinetic energy of 3/2 RT. If I raise the temperature, then I'm going to keep moving that up, and the energy and randomness in the motion is going to increase. And I'll get to a point where that molecule gets out of its own cavity and moves into an adjacent cavity. What did I just do? I heated it to its melting point, and it melted. Okay, now I keep heating it, its average kinetic energy increases and increases and increases to some temperature at which that molecule bursts out of its cavity and goes out free. What did I just do? I boiled the liquid. So at any given temperature, the average kinetic energy is 3/2 RT, and it doesn't matter whether it's a solid, liquid, or a gas. I've yet to see a book that explained that correctly at freshman chemistry. Uh, and you go to physical chemistry, then they'll tell you the details, but that is true. All of the books will tell you about this for gases, but it's also true for liquids or solids as well. Okay. Uh, now, I told you the average kinetic energy, 1/2 mv squared, is equal to 3/2 RT for every substance in any phase. Now, so if the temperature is constant, if I had two different gases at the same temperature, I could say 1/2 m1v1 squared is equal to 3/2 RT, and 1/2 m2v2 squared would be 3/2 RT, so they're equal to each other. So I get this relationship, and that's what Graham's law says. The rate of a fusion of a gas is proportional to the square root of its molecular weight. So it's inversely proportional to the square root. So this velocity goes with this mass, and this velocity goes with this mass. And there's a checkpoint on this, but it's going to do exactly the same thing we did there. Oopsie daisy. I've got to return after each one of these or I'll go somewhere else. Now, remember I told you about Pearson's law of stuff? Well, I shouldn't have claimed it's mine. It's called Fick's law. And it says that the flux of something, the movement of something out of one area to another area, the flux is how much moves per cross-sectional area. So imagine a window, and you're thinking about the heat. Well, you've got high temperature on one side of the window, maybe outside, and a lower temperature on the inside when you're in the house. So heat's going to try to get through that window. The rate of flow of the heat through that window depends on how big the window is. The bigger the window, the more heat will pass through it. That makes sense. But it depends just on the temperature difference. The difference in temperature from the hot side to the cold side. It's going to flow from the hot side into the cold side. That's the reason for the negative sign here. The flow is opposite to the direction that we are taking as positive. So, and the difference in the concentration. In the case of heat, it's the difference in temperature. It would be the same thing if I imagine some kind of a little window in a solution. And on one side of that window, maybe imagined window, I've got, say, sodium chloride at 6 molar. On the other side of the window, I've got sodium chloride at 5 molar. Well, it's going to flow from the 6 to the 5 through that window. And if I double the concentration difference, I double the rate at which it occurs. So this is saying fixed, as I said, stuff flows from where it is to where it's not. It flows the opposite direction to concentration increase. That's the reason the Fick's law has a negative sign here. It flows from high concentration to low. And we're thinking increasing is low concentration to high. Okay? That's called Fick's law. And here's an illustration of how it works. If I've got my little imagined window here, and I've got molecules at some concentration here, and molecules at showing a lower concentration over here, then I'm going to get flow in each direction, but the flow from the high to the low is greater than from low to high, and the difference is just proportional to this concentration difference. So the net flow is going to be from high concentration to low concentration. So that was what I call Pearson's law of stuff. Stuff flows from where it is to where it's not, and it doesn't matter what kind of stuff. Anything that has a different concentration in one area than it has in another area will flow from the high to the low. Now, let's look at the corrections for real gases. We did a problem a while ago and we said it was impossible to cool carbon dioxide to the temperature we calculated because it freezes before it gets there. Well, what is it about gases, real gases, that makes them not behave like ideal gases? Well, the properties of an ideal gas are there are no forces between particles. We argued that already. And that the particles have no volume at all. Now, we know that's not true. It can't be true. But the way we treat it in an ideal gases assumes that there's no volume for the molecules. Because when we put V in our PV equals nRT, we put the volume of the container in. If the molecules had volume, there would be places in that container where another molecule couldn't go because there's molecules already there. So we've assumed that the particles of the gas have no volume so that we could plug in the volume of the container. Now, real gases can behave like ideal gases if you do high temperature and low pressure. Let's think about that. When molecules come together, let's suppose you've got some weak forces between them. Well, if you imagine taking a molecule, right now I'm holding my two fists together. And my left fist is one molecule, my right fist is another one. And they're attracting each other and sticking together. Now, I imagine pulling my right molecule, the one my right fist, away. I'm using up energy in doing that. But there's a certain fixed amount of energy. When I get them to infinite distance, they don't attract each other at all. There's no work being done there. It's only right during the first initial phases of separation that I'm going to do most of the work. But any pair of molecules, no matter what the force happens to be, there would be a fixed amount of work it would take to separate them. Now, if you compare that energy to the kinetic energy, that means if I get the temperature high enough, when the molecules come together, they will hit with enough force, they'll completely bounce off as if that attractive force weren't there at all. So at high temperature, they're going to have a kinetic energy much greater than the energy I imagine in pulling the two molecules apart to infinity. So high temperature would favor a behavior for a real gas like an ideal gas because it would make the attractive forces unimportant. Now, what about, I said low pressure. Why would that be more ideal? Well, at low pressure, molecules are very far apart. At high pressure, you push them close together. If you push them close together, the forces take over. And they don't behave like they're ideal if there are forces between them. If you're at high enough pressure, that's going to become important. But at low enough pressure, the average distance is so far away that there's essentially no force between the particles at that distance. So low pressure, high temperature, a real gas ought to behave like an ideal gas. And this is the argument, and I'm showing it on the cartoon here. Here's my two fists I was talking about a while ago, and I'm separating them. And I'm going to plot the energy versus the distance of separation, how much work it takes me to separate them for a certain distance. Well, as I start pulling them out, I use some energy to do that. And then as I pull them further, I use some energy, but I'm using a little less energy than I did the second time. And they're further apart now, and I pull them out the same distance again. It takes a little less energy. And as you keep doing this, and when I get to infinity, this is the amount of work it would take to separate them all the way to infinity, is where this would come out here. So this amount of work would I would have. If my kinetic energy is a lot greater than that, this molecule is going to behave like an ideal gas. The kinetic energy goes up, remember, proportional to the temperature. So the higher the temperature, then If the kinetic energy is greater than that limit, it behaves like an ideal gas. So that's at high temperature. Low pressure, the average distance, if that's much greater than the diameter of the molecule, then the forces are small. So the molecules are far enough apart, they wouldn't behave, they would behave ideally, and they wouldn't show any variation in Boyle's and Charles' law, things like this. Now, here's a cartoon that illustrates that. Here's a container that has molecules in it. Now, if I imagine taking all of those molecules and compressing them till they touch each other and make some layers down here in the bottom. If this is such that the volume of these molecules is insignificant compared to the volume of the container, then the behavior is going to be ideal. And the volume of the container gets bigger as we reduce the pressure. So at low pressure and high temperature, we'll come up with something that is ideal. Now we can take those two ideas and fix the ideal gas equation to make it predict the correct behavior of real gases. And it's called the van der Waals equation. And what it does is it makes corrections for both of those two forces. It's going to correct the pressure because the pressure, as we increase the pressure, we're going to get the molecules close enough together that they're going to start attracting each other. So we need a pressure correction for that to happen. Now, the pressure is caused by collisions with the container walls. So let's look at this. I've got a molecule in a container. This is the two walls. I'm just going to go between these two walls. You could think of this three-dimensional thing, wouldn't matter. It'd just be the same thing as happening in this case. So for this molecule to move through the container, it's going to go in, it's going to hit this wall, it's going to bounce off, it's going to hit this wall, it's going to bounce off, and then return to roughly its same place. Let's back that up. Now, so it's going to have a certain number of collisions per second with the wall that determines the pressure at the wall. Now, let's suppose there's another molecule in the container, and the molecule can go through like that. It can miss that other molecule. It come back, maybe come back here. It hits it and bounces back and goes to the wall. The number of collisions per second increased because it hit this molecule and returned and didn't have to go all the way over here to return. So the presence of this extra molecule makes this one hit the container more likely and more frequently and causes the pressure to go up. Now, so I need to do something to correct the pressure. It's going to be higher than the ideal gas pressure by this correction I have to make for collisions that take place. Now let's look and figure out the probability. There's a projectile, that's one of the molecules, and here's a bunch of target molecules. What's the probability that this projectile will hit one of these target molecules? Well, it's proportional to the concentration. The higher the concentration here, the more likely it is one of these is going to hit one of those. So the probability of a collision is proportional to the concentration of the targets. Now, let's think of it this way. Here's a bunch of projectiles, and here's a target. What's the probability that at least one of these projectiles hits that particular target? Well, it's proportional to the concentration of the projectiles. So, probability of the projectile hitting a target is N over V. The probability of a single projectile hitting one of many targets is N over V. A projectile hitting a target is a collision. So the number of collisions is proportional to this probability times this one. That is, you've got two events. Say you've got a die. It's got 6 digits on it. 1 through 6. 6 spots on one side and 1 through 6 on the other. 1, 2, 3, 4, 5 on the other side. And you've got a coin. It's got a head and a tail. what's the probability if you roll a die and flip the coin that you'll get a 3 and a tail? Well, what's the probability of getting a 3 on a dice? Well, there's 1 3 and there's 6 positions, so it's 1/6. What's the probability of getting a tail? Well, it's 50-50, 1/2. Half the time you should get tails, half time heads. So 1/6 times 1/2, 1/6 times 1/2 would be 1/12, would be the probability that you would get a 3 and a tail. Okay, well, that's what we're doing here. What's the probability proportional to N over V times N over V? So the likelihood of collisions between particles and causing an increase in the pressure is N squared over V squared. And I said it's proportional. This is just a proportionality constant. So that when I take N squared over V squared and multiply by this number, I get units of pressure. That's just a conversion factor. Okay, now we've got a pressure correction to the ideal gas equation that takes into account concentration and collisions between particles. Now let's correct for the volume of the container. Well, that's an easy correction. We've already looked at that. If I take all of these molecules and compress them down to here, this would be the volume of 1 mole of these molecules if they were touching each other. And so I need to correct the pressure, the volume that this molecule has by the volume of the container minus the volume of the molecules. So that's just going to be proportional to the volume of a mole of molecules. This is a number of moles, and this is the volume of 1 mole. And that'll be different whether it's carbon dioxide or whether it's oxygen or whether it's helium or nitrogen. The volume of the molecule would be different. That's what that B constant is. And so now when I have a correction, it's called the van der Waals equation, P plus A N squared over V squared times V minus NB equals nRT. Now you saw how simply we made that correction. It's a complex looking equation, and we've lost something. In the ideal gas equation, we could apply that to carbon dioxide and nitrogen and ammonia and helium, anything we want to. And I don't have to have a particular constant for the particular gas. You see, the only thing that changes from one gas to another in the ideal gas equation is the molecular weight, and therefore the number of moles in a sample. So I don't need to know what the gas is if I use the ideal gas equation. It's not for real gases, although we apply it to real gases at high temperature and low pressure. And high temperature generally means high compared to its boiling point. If I take water vapor, for example, if I take water vapor at any temperature above 100 degrees C, it's going to behave, high temperature, say 200 degrees C, it's going to behave like an ideal gas. I can use the ideal gas equation. It'll be okay. If I'm dealing with water vapor, its vapor pressure is somewhere around 23 torr. So if I'm at a pressure like 760 torr, I don't need to worry about it. It's going to still behave like an ideal gas. So around reasonable pressures, 1 or 2 atmospheres, and a temperature above its boiling point, it works okay. But if you use the ideal gas equation on water vapor at 25 degrees and 25 torr, that's going to be really close to its own vapor pressure at 25 degrees. It's going to be more like liquid down there. So at temperatures below 100 degrees and at pressures down there around 25 or 30 torr, it's not going to behave right. It needs to be a much higher temperature in order for that to happen. So when we talk about high temperature and low temperature, the comparison really for a real molecule is, are you above its boiling point? If you're way above its boiling point, you can use the ideal gas equation. If you're around its boiling point or lower than its boiling point even, you can use the van der Waals equation. The weird thing about this is it works so good. You can even do pressure volume relationships in liquids. Will behave this equation pretty well. So this is a really great correction. And the only thing we've lost is we have to put in a constant that's for carbon dioxide for A and B. If I want to use this equation for water vapor, I'll have to put in a constant for water vapor A and the water vapor B. So this equation, you have to have some experimental data to help you if you're going to use this one. And textbooks give you a collection of these A and B constants that's been calculated and saved so that we can use the van der Waals equation for lots of different gases. Okay, and it just worked very good for even fluids. As I told you, it works within the liquid phase even. That's really weird. Okay, what's the pressure of a vessel containing 5 grams of helium and 5 grams of argon in a 1.5 liter at 50 degrees Celsius? Okay, both gases are ideal. The total pressure should be the sum of the partial pressures. That's Dalton's law. And the pressure of each one, pressure of hydrogen is number of moles times RT over V. The pressure of the helium would be the number of moles of hydrogen, of helium is 5 grams, molar weight is 4, it's 1.25 moles, and the temperature is 323 Kelvin. And so I get 1.25 times 0.081 times 323 divided by the volume of the container is 1.5. It's 22.1 atmospheres. So this gas would have 22.1 atmospheres. And what would be the partial pressure of the helium? Okay, well, if I'm doing argon, we got 5 grams of argon, and the molecular weight is 40. So if I divide 5 by 40, I get 0.125 moles. Put it in the ideal gas equation, same temperature and pressure and volume, I get 2.21 atmospheres. So the pressure of the argon would be 2.21, pressure of helium would be 22.1. Total pressure is the sum of the partial pressures. Add these two together, you get 24.3 atmospheres. Gas mixture contains 5 grams of helium, 5 grams of argon. Partial pressure of helium is 625 torr. What's the total pressure in the mixture? Okay, both gases are ideal, so I can use Réal's law to solve this problem. Partial pressure of helium is the mole fraction of helium times the total pressure. The pressure of the neon of the helium is, okay, I can get the number of moles. I've got 5 grams, the molar mass is 4. I got 1.25 moles. If I look at the argon, I've got 5 grams of argon, and the molar mass is 40. I got 0.125 moles. The temperature is that, and so the mole fraction is going to be 1.25 divided by this plus this is 1.375. Mole fraction of helium is 0.9091, and I can plug that number in, and the pressure for the helium is right there, 625. That's the mole fraction. I can solve for the total pressure. Total pressure is 688 torr. So now let's back up. So I could get the pressure of the other gas in it. This was, we used the pressure of the helium, so I could get the pressure of the argon. Well, it's just the difference between this one and the total. So 625 is subtracted from 688. The difference would be the pressure of the argon in the container. What's the molecular weight of a gas if that many moles of gas diffuses through an opening in 65.2 seconds? If the same pressure of neon is placed in the same chamber, 0.35 moles diffuse in 55.3 seconds. Okay, this is rates of diffusion of two different gases. That's Graham's law. So this is the relationship from Graham's law. Remember now, it's an inverse. The heavy molecules travel slower. So they go inverse relationship. And I got the data that I can put in. The velocity of my unknown gas, it takes 0.22 moles, fused in 65.2 seconds. So I can get the rate of effusion is 0.00337 moles per second. The velocity of effusion for the of the neon, it takes 0.35 moles if used in 55.3 seconds. So it's that number. So this divided by this equals the molecular weight of my unknown. Number 2 was my unknown. And molecular weight of the neon is 20.18. Solve for that. I can get the molecular weight of the unknown. Molecular weight of the unknown is 71. Now at this stage, you remember, I keep pointing out the inverse relationship up here. Sometimes people reverse one or the other side of this and mess it up. If you do, you'll come up with a number that doesn't make sense. Now, looking at this, the rate of effusion of my unknown gas is slower than the neon. The molecular weight should be higher. So I should get a number here that's greater than 20.18. If I don't, I've made a mistake. And probably the place the mistake was made is back up here and putting that relationship in wrong. How long will it take for 0.16 moles of SO2 to effuse from a chamber? If it takes 35 seconds for 0.25 moles of nitrogen to effuse through the same chamber. Okay, again, Graham's law. Again, we're going to write the relationship. V of SO2, we don't know. Velocity of nitrogen, we do know. 0.25 moles effused in 35 seconds. So it's 0.00714 moles per second. So I've got that number. I can solve for this one. Molecular weight of my SO2, 32 plus 2 times 16 is 64. Remember, these go opposite. And 28 for the molecular weight of N2, 2 times 14. Do the math. I solve for the velocity. Velocity is 0.00472 moles per second. Now, to check, SO2 is heavier than N2, so it ought to travel slower than the N2, and that's what we got. We got a number that was smaller than the effusion rate for the N2. So again, it's the way to check. The time then is the number of moles divided by the number of moles per second is 33.9 seconds. Calculate the pressure 50 grams of CO2 should exert in a 275 milliliter container at 27 degrees, and use the ideal gas equation and the van der Waals equation. So let's do the ideal gas equation. Well, here's the numbers. The constants are this and this for CO2. The A constant is 3.59 in the appropriate unit, and the B constant is 0.0427 in its appropriate unit. Ideal gas equation, PV equals nRT. Pressure is 102 atmospheres if it's an ideal gas. It's a van der Waals gas. Now let's see. Now this looks kind of messy, doesn't it? P plus A n squared divided by V squared times my n squared. A n squared over, no, V squared, n squared over V squared. V minus NB, there's my number of moles. There's my B constant. This was my A constant here. And plug together, that equals N, 1.14. R times the temperature is 300 Kelvin. It was given in Kelvin, so I don't have to convert anything here. It's already correct unit. I can solve that for P. 62.4 atmospheres. Okay, now, does that make sense? Think about it. if the molecules are in there and there's forces of attraction, they're going to be pulling each other closer together. So if they pull each other closer together, they're going to exert less pressure than they would if they didn't have that pull. So generally, the ideal gas pressure of the van der Waals pressure is going to be less than the ideal gas pressure, because we've not taken the forces of attraction into account here, and we have down here. So the pressure should be less than. Remember, we added something to the pressure up here in the equation. Now let's think about the ideal gas equation and the van der Waals equation, and let's just be real. Let me get over here and show you the point. Be practical. Stop the sharing so you can see this. Now, yeah, the van der Waals equation, you do have to memorize this now. P plus A n squared over V squared times V minus NB equals NRT. Now, it is kind of messy to do this calculation. You know, it's kind of messy. But I can solve for P pretty easily. I would take nRT, divide by V minus NB over here. That gets rid of that term. And I'm going to subtract AN squared over V squared from both sides. So it would be nRT. Well, I'll turn that thing off. I would take nRT divided by V minus NB in parentheses minus AN squared over V squared. I can solve for P pretty easily. I could solve for T even easier. I got this term times this term divided by NR. So I can give you a problem that says what is the pressure, or I can give you a problem that says what is the temperature. But I can't do volume very well, because if I want volume by itself, you see I'm going to have to multiply. I'd have to get a common denominator here, which would put a V squared here and the whole thing over V squared. And then to get rid of that V squared, I'd have to multiply through by V squared. So I'd have to put this thing over V squared, and then I could just cancel it out of both terms to get rid of it. But what I would wind up is a V squared times a V term would give me a cubic term. And I'm going to have an equation that's going to be of the some constant n1 V cubed plus n2 V squared plus n3 V to the first power plus a constant, and n3 n4, let's say, equals 0. I'm going to have a cubic equation to solve, and that's kind of difficult. And you'd have to put it in the standard cubic form if you have a cubic solver in your calculator. So honestly, I'm not going to ask you for the volume, but I can ask you for pressure or temperature, either one. And it's a reasonable problem. Temperature is a little bit easier than the other one. Now, I think we're going to pick up a checkpoint on this in a minute, that I do want to work with you let's I need to escape out of here. I need to go back to screen share. And okay. Now, so this is what we were doing. We did this, and this is the problem I was telling you. I think I need to, I've got to get PowerPoint back running, and I've got to get back to where I was. Oops, previous. I want to go here. Now, so I've got a problem here. 2.2 mole sample of an ideal gas is found to occupy 25 liters at 740 torr at some temperature. What's the temperature of the gas in degrees Celsius? At what temperature would the same size sample of van der Waals gas occupy 25 liters at 740 torr? So this is a problem I told you I'm going to go back and work with you. So let's go back through and we'll solve this one, and then this is the ending of the material. We'll take a little break, and then I'll come back and do the practice quiz with you. Okay, so good. All right, now the first problem, we had N is going to be 2.20 moles of some gas. The volume is going to be 25.0 liters. And the pressure is going to be 740 torr at some temperature, and we're going to solve for the temperature. So if we've got an ideal gas, I've got PV equals nRT. And so temperature is going to be equal to P times V over N and R. Okay, so that we just need to plug our numbers in. So the pressure is 2.2. The volume is 25 liters. I'm just checking to be sure there's the correct unit. Pressure 740 torr, so that's 740. The 760 that would go down here in the denominator of the denominator, I'm going to put it in the numerator, 760. Put it down here and put a parenthesis around if you feel more comfortable. And R is 0.0821. Okay, so there's my numbers. 2.2 times 25 times 760 divided by 740 and divided by 0.0821. Okay, and double checking my numbers, 2.2 times 25 times 760 divided by 740. It looks like I entered it correctly. So for this answer, I'm getting 688 and 0.0205, bunch of digits over here. And that'll be degrees Kelvin, or just kelvins. They tell us not to use degrees. We're supposed to say kelvins instead of degrees Kelvin, but that, I don't know. There are people who actually worry about things like that. I'm not one of them. Okay, number 2. What temperature would the same size sample of a van der Waals gas with an A equal 3.59 and a B is 0.0427 occupy 25 liters at 740 torr? Okay, now I've got to write my van der Waals equation. P plus A N squared over V squared quantity times V minus NB equals NRT. Now, it's telling me to solve for T. So I'm going to divide the whole thing through over here by N and R, and that will divide this over here, divide the NR out, it'll be the T. So my temperature is going to be P plus AN squared over V squared times V minus NB equals nRT. Okay, now I'm going to do exactly what it shows right there in that calculator. And I'm not going to take P plus AN squared over V squared divided out equals and write it down and then do V minus NB. subtract it, write it down, and then multiply the two numbers together and divide by n and divide by r to get that answer. I'm going to do that calculation right there on my screen. So I'm going to put the numbers in right here, and then I'll show you how we're going to go about doing this. See, I have to put n in there several times, so I'm going to actually put the n in first. So it's P, my pressure is 740 divided by 760. I can't move it upstairs right now. I have to do it just like that. A is 3.59 and N is 2.2 and that's squared, and the V is 25 and that's squared. And now that's that first term. The second term is V, that's 25, minus N is 2.2, and the B constant is 0.0427, like that. And then this whole thing is going to be divided by N as 2.2, and R is 0.0821. Now my temperature is equal to that crazy looking thing there. But let's keep our head about us. And here's what I'm going to do. I'm going to take my my calculator, and I'm going to put N in the calculator first. It's 2.2 because I got to put that thing in many times. Okay, so my calculator now has 2.2 for N. So here's what I'm going to do. I'm going to take 740 divide by, no, wait, I need a parenthesis. Let me back it up. I said I'm going to do exactly what I say. Parenthesis, 740 divided by 760 plus A is 3.59 times answer, second answer, squared, that's 2.2 squared, divided by 25 squared, close my parenthesis. Now I've got that term in the calculator. Now I'm going to take this one, times another parenthesis, 25 minus minus second answer, that's my N, minus 2.2 times my B, times 0.0427, and now I need a close parenthesis. Now I'm going to divide that by N, that's second answer, and divide that by 0.0821. Now, if I haven't screwed up, my calculator has all of that stuff in it. I didn't have to write anything down. I just copied that exact equation into my calculator. If I didn't do some silly calculation wrong, I push equal, I should get the answer to this. And what I come out with is 138.096 Kelvin as the van der Waals temperature that this gas would occupy. So, you know, I could have made a mistake in here somewhere, and that might not be right. But I wanted to illustrate that you don't need to do these things in a whole bunch of steps. Now, I would have done that, and if I'm looking at a multiple choice question, if that's not one of the answers, I know I just entered some data wrong somewhere. So I'm just going to double check and go back and enter it in again. The reason I put the N squared in there, or the N in there first, so that I could keep pulling the answer up, it would have been just as easy to put the 2.2 in here. But sometimes when we're doing problems, they might give you the number of grams. And if you got the number of grams, you have to calculate the number of moles. So if you got the number of moles already in your calculator for the first problem in ideal, and it was given in grams, and you calculated that value, well, you calculated the moles up here. So you can keep that in your calculator. And then just put it in every time you see it here. That's n squared. That's your calculator, your number of moles squared. And V minus NB, you got your number of moles again over here, and so forth. And then N was down here. So it's sometimes easier to do that. And if you do it all in one step like that, it takes a little time to enter all of these things in. The critical thing is you have to enter these parentheses in just like you see them up here. And remember to put the time sign right there between them. And then do the math. And when you do that, you should get one of the answers on the exam. Chances are, if you don't get the correct answer, you're not going to get one of the other foils either, I'm guessing, because of the complexity of that calculation. So just if you don't get one of the answers, do it again, and until you do. And if you keep doing it and you keep getting the same answer, you might want to, if we were in class, you'd want to raise your hand and say, Dr. Pearson, I don't get a correct answer for number 17 or whatever it is. And then that could be fixed. In this stage, there's not much of a way to correct for that while the test is going on, but you can tell me about it. And like the last test, if there's a mistake, I'll correct it on the key for the grading so nobody gets hurt by it. Okay. All right. So that's essentially the ending of all of this unit. And I think we need to take a little bit of a break, and then I'll come back after this and we will work the practice quiz out that's due on Monday. Bring back up. And then let's go here. Okay. This is the last quiz for the season. So we'll, let's see, let's make this a little bigger for you to see. And there we go. All right. Okay. I guess that's all right. Okay. All right. So I'm hoping all of you have a copy of the practice exam. And when I work out the problems, I want you to see what I'm doing. So I'll do them over here on the side on the camera. But if you have a copy, maybe it'll be a little bit easier. In general, when I work out the problems, I'll copy off enough of the answer or the problem so you could tell what it is without actually having to go back and look at it. So I'd like to do it that way and not have to jump back and forth between the two, because I so often forget to do that. Now, the first problem on this test is to calculate the mass of carbon. So number one is it's going to ask me what is the grams of carbon in 1 milliliter of 0.125 molar, and the compound is Fe3 FeCN6 2. Okay, so This is the compound that we're doing, and we want the amount of carbon. That's a parenthesis right there. Okay, so um, this is my number and my unit. So what I've given essentially is data for the number of moles of the compound. So I'm going to take 1.00 times 10 minus 3, 1 milliliter, and the molarity is 0.125. Now that gives me moles of compound. Now, what I want to do is convert from that unit, moles of compound. The problem says grams of carbon, so I'm going to put grams of carbon in the numerator. And now I'm going to have to put the units in there that I know if I had 1 mole of that compound, I know how much carbon I've got in it. Okay? There's 2 of these whole things, and each one of these things has 6 of these things, and each one of these things has 1 carbon. So the number of carbons is 2 times 6. That's the number of moles. The mass is 12.01. So that is the setup. So let's go back over here and make it a little bigger so you can read my writing. 1.00 times 10 minus 3. I'm going to multiply that by 0.125. I'm going to multiply that by 2 times 6 times 12.01. That'll be grams of carbon. And my 1 mole of the compound is going to cancel out. So this was moles and the moles cancel. So there's my math to do the problem. So I take 1 with an exponent of minus 3 times 0.125 and times 2 times 6 times 12.01. And the answer I'm coming out with is 0.0180015. That's the numbers I see on my screen. And that's going to be response C on the test. So this is similar to problems we've worked before. The only thing we've added is that volume times molarity equals moles. And then we use that in solving this problem. Now, number 2 is a very, very practical problem. When you get to quant, I am absolutely sure you'll have to work a problem like this. It's a problem that we have generally stock solutions of all of our strong acids and bases, generally, well, anything that's liquid. We'll buy it from a chemical company, and it comes in, and on the label, it will give you the percentage of the compound that's in that solution and the density of the solution. Now, from that, you can get the molarity. And this problem says, what is the molarity of a solution of chloric acid that is 82.9% chloric acid, and the density, right, rho, is equal to 1.45 grams per milliliter. So that's the density of that solution. We want to know what's the molarity of it. And when it said what's the molarity, remember what I told you. When you have a question asking for the molarity, you're going to write down the definition. Molarity is the number of moles of the solute divided by the number of liters of the solution. And I hope you also remember what I told you about what is the best number in the world to divide by? 1 liter, right? Molarity is the same whether you make 1 liter or 2 liters or 1 milliliter or 1 drop. The molarity of all of the same are the same because it's the ratio of moles per liter. So the easiest calculation is I'm going to have 1 liter. Now, what did that tell me? Well, from the density, I know it's 1.45 grams per milliliter. So I'm going to change this to from liters to milliliters, and milli is 10 to the minus 3, so this is 10 to the minus 3 down here as well. So now that's my conversion. So I've got 1 divided by 10 to the minus third. Now, that is the liters of the solution that goes here. So a liter of the solution is 1 times 10 to the third. If I divide by minus 3, I get to the plus 3 milliliters. Now, the density tells me I can convert that to the grams of the sample. Okay, so let's do that. I know that there's 1.45 grams of that solution in 1 milliliter. So when I do this math, I'm going to come out with the grams of the solution. Okay, so I'll just go ahead and do that intermediate calculation while we got. So we got 1, we got 1,000 times 1.45 divided by 1. So I've got 1,450 grams of the solution. Well, I want moles of solute. So I've got to get from solution to solute. I can do that with a percentage. Because if I had 100% of 100 grams of that solution, it would have 82.9 grams of solute. That's from the percentage. So I want to take this number, multiply by 82.9, divide by 100. So I take the number I've got on my screen. I want to multiply it by 82.9, and I want to divide it by 100. I'll go ahead and do that math. And let's get another piece of paper over here. Now, the number I got was 1202 grams, 1202.05 grams of the solute. Well, I don't want grams of solute, I want moles of solute. So I've got to convert from grams of solute to moles of solute. So grams of solute here and moles of solute here. Well, let's see how much 1 mole weighs. Now, way back up here, it says this is chloric acid. So that has to come from chlorate ion, which is ClO3 minus. The acid would be the HClO3. I'd need 1 of each to balance charge. So this is the formula for chloric acid. It's got 1 hydrogen. That's 1.008. That's 1 chlorine is 35.45 something. And 3 oxygens is 3 times 16.00. So my molar mass is the sum of all of these weights. And, you know, I'm going to tell you how I would do it. See, I still got this number right here on my screen. All I need to do is divide by the sum of these. This plus that. So that's what I'm going to do. I'm going to put a parenthesis. I'm going to do a divide. I'm going to put a parenthesis. Divide by 1.008 plus 35.45 plus 3 times 16 and close my parenthesis. And now I've done that calculation. It would be like adding all of these numbers up and putting them right there. And so now I should be able to push equal, enter, and I get as an answer 14.23251794, and I've not taken anything off the calculator. I could do my round off, and my percentages up there was 89. That's a 3 significant figure, and I believe the density was given to 3, right? Yeah, 1.45. So I should stop right there. So I'm predicting 14.2 will be the correct answer, and that is response D on the quiz. Now, I hope you'll practice a couple of these, because I really personally believe this is one of the most important ideas that you're going to do on molarity, is a calculation like this. Because I know if you stay in chemistry even through a minor, you're going to wind up taking quant probably. And I know you have to make up your own solutions in quant. And I know they're going to give you a bottle of concentrated hydrochloric acid, and they'll give you you can't just say that that's 12 molar. It probably is close to 12 molar, but the individual bottle you've got will give you the density and the percentage of hydrogen chloride in that bottle. And you'll have to calculate to 4 significant figures at least what the molarity of that solution is. And so this is a very, very practical problem if you're going to ever do anything with chemistry. In fact, I would guess if you do anything with chemistry, you're going to be dealing with molar solutions, and you're probably going to have to do a problem like that. I think it's very important. Hint, hint, hint. All right, let's see what we got for number 3. You can ask anytime you want to if you have questions. Don't let me go on, or be sure if you see me make a typo or cut or an error, you call that to my attention. We'll save some time. Okay, now here's a stoichiometry problem, and it's obviously going to involve some molar solutions. The problem is, I'll read it to you. It gives a balanced equation: 3 propane, C3H8, plus 20 chromic acids goes to 9 carbon dioxides, 10 chromium-3 oxides, and 32 waters. And the problem is, what mass of chromium-3 oxide would form by reacting 0.155 grams of propane with 5 milliliters of 3.75 chromic acid. So the things that we're dealing with in this problem is the 3C3H8, the 20 H2CrO4, and we're going to go to 10 Cr2O3. Okay, so that is my equation. And now let's put in the amounts. We have 0.155 grams of propane. And I'll just complete this stuff for propane in the balanced equation. We have 3 moles. The molar mass is given in the problem at 44.1. So the number of grams in the balanced equation is 3 times 44.1. That's going to give me one of my rebalancing factors. This says 5 milliliters, so I'm going to write that as 5.00 times 10 minus third That's milliliters. And I want to multiply by the molarity. That's 3.75. That'll be moles. The equation is showing 20 moles. Okay, that's my other rebalancing factor. And we want to know what mass, how many grams. The equation is showing 10 grams, and the molar mass is given at 152 grams. Okay, now let's do our rebalancing factors. I'm going to divide these out, this divided by this and this divided by that. Let's see what we get. I take 0.155, divide by 3, and divide by 44.1. Yes, I'm coming out with this one is 0.001171 and some other digits. Now I'm going to take 5 with an exponent of -3. I'm going to multiply that by 3.75, and I'm going to divide it by 20. And I get, in this case, 9.375 times 10 minus 4. This is 10 to the minus 3. This is 10 to the minus 4. This is going to be my limiting reagent. So I take that times 10 times 152. So that number times 10 times 152 should be my answer. And I'm getting 1.425, and that'll be in grams. I'm allowed 3 significant figures. My calculator shows no digits after the 5. So my rule of round to even would just drop the 5 and leave that as a 2. That's already an even number. So the correct round off should be 1.42 grams. That's response A on the test. So that we did get the right answer. Let's go on to number 4. Number 4 is the same equation, but it's asking some other problems. So let's see how we go about doing this one. Okay, so number 4, it says what volume of 3.25 molar chromic acid is required to make 1 gram of chromium-3 oxide. So there's 2 things involved in the problem. There is the 20 chromic acid is the H2CrO4, and we're going to make the chromium-3 oxide, Cr2O3, and we want to know how much of this, it's asking for what volume of some molar concentration would I need if I wanted to make 1 gram of this. Okay, now I'm going to work this in moles. If it's asking me quantity, it's easiest to do it in moles, and then we'll do grams later if that's what we need to do or whatever we need to do with it. So I'm going to do moles. If I want the answer in moles, then the equation is showing 20 moles. That's my setup on that side. Over here I've got grams, so that's going to be 10 moles, and the atomic weight was given at 152 grams. So this in the same unit gives me that. There's my rebalancing factor, 1 divided by 10 by that, divided by that. So I'll just put it over here, 1 divided by 10 and divided by 152. That's the RBF. My answer is the RBF times what under the question mark is 20 moles. Now, the answer wanted volume of some molarity. So let's go ahead and do this calculation and then I'll do the unit conversion. So I want to take 20 and divide by 10 and divide by 152. Same thing, 20 divide by 10, divide by 152. Okay? I'm coming out with, I'm going to need 0.01315 and a whole bunch of other digits here, moles of the compound. Now, volume times molarity is equal to moles. So volume I don't know, but I do know what the molarity is. The molarity is 3.25. So I can solve for volume. Is going to be this answer divided by 3.25. Answer's on my screen, divided by 3.25. So I'm coming out with a volume of 0.004048583. That's all the digits I see on my screen. What's the units? Liters, that's right. Now, I'm looking at the answer. I don't have liters given. So I've got to convert from liters to milliliters. Milli is 10 to the minus 3, so I need a 10 to the minus 3 down here. So if I take my answer and divide by 10 to the minus 3, I should get the final answer. Divided by 1 with an exponent of minus 3. I'm getting, I got an answer of 4.048582996 milliliters. And I have 3 significant figures, I think. 1.00 grams is the only significant figure. And then I've got my molarity was 3.2. It's 3. So I'm going to round off here. So it's 4.05 milliliters. And that is response C. All right. And moving right along. Got the same problem. And we're going to do another stoichiometry problem. But this one is also going to include gases. So, yes.
Happy birthday, Mom Jack. I literally thought about that. I was like, what if Hannah did something from Jack? Donna made me a cake. She walks out with a candle. Are you on FaceTime?
Okay. Yeah, somebody may need to mute your mic if you haven't already. Okay. All right. Number 5 is the same equation. It says what volume of some molarity chromic acid is required to make 1 liter of CO2 at some temperature and pressure. So the chromic acid, again, we've got 20 H2CrO4. And in this case, we're going to carbon dioxide, and there's 9 of them, CO2. So these are the 2 things in the balanced equation that pertain to this problem. And what I want is 1 liter of this gas at 25 degrees C and 735 torr. Now, I'm going to use the ideal gas equation to convert this to moles. And the equation is showing 9 moles. Okay, so I got a little sidebar calculation to do there. Then I'm going to go over here and it's asked how much of this. So I'm again going to say how many moles. And the equation is showing 20 moles. Okay, now I can do my problem after I do this first little sidebar calculation. So for a gas, N is equal to P times V over R and T. So my pressure is 735 divided by 760. the volume was 1 liter, and R is 0.0821, and the temperature is 25 plus 273 is 298. Okay, now, so let's do that calculation. This divided by this, divided by this, and divided by that. So there we go. We take 735 and divide by 760. That puts it into atmospheres. Now I want to divide that by 0.0821 and divide that by, I'm going to go 25 plus 273.15 because I don't know what I did on the real problem. Okay, so what I came out with now for my number of moles in, I got 0.03951 5088, a whole bunch of digits there. So I'll get my rebalancing factor. It's going to be the number of moles I got up here, 0.0395 and a whole bunch of digits divided by 9. But I can do that now on my calculator because I still got this number in my register on the calculator. So I want to take this number that's on my calculator and divide it by 9. So I divide by 9 and I get my RBF for this problem is 0.0043888, whole bunch of some more digits for the rebalancing factor. Now I want to get the number of moles. So my number of moles of the chromic acid is going to be equal to the RBF, this number, times what's under the question mark in my problem is 20 moles of the compound. So I've got my rebalancing factor. I need to multiply that, this times the 20 moles, so times 20. And what I come up with now is the number of moles of the chromic acid is equal to 0.08779 and some more digits, but that has to equal to the volume times the molarity. I know what the molarity is. It's 3.25. So I want to divide by 3.25. So the volume is going to be this number that it's on my screen divided by the molarity is 3.25. So I want to divide that by 3.25. So I come up with 0.027014686, and that's in liters. I have to convert that to milliliters because the answer is given in milliliters. That's liters. I need a 10 to the minus 3 down here to be the 20 milliliter up there. So I need to divide that by 10 to the minus 3. So I divide by 1 with an exponent of minus 3. And I'm coming out now with the volume in milliliters is 27.01468,459. That's all my digits. And that's now in milliliter units. And I've got 3 allowed. So the answer should be 27.0 milliliters. That is response D. So we're good. Okay. You see, the only thing we've added in doing this stoichiometry is we added volume times molarity equals moles, and we used N equals PV over RT for gases. So we just added that little caveat, but we worked the stoichiometry just like we always did. But what we're going to do always first is we're going to work the problem in moles. And then we'll go from there. Using those definitions, we'll go from there. All right, number 6. A mixture contains 5 moles of nitrogen. Nitrogen gas is N2. And it contains 8 moles of oxygen gas, that's O2. Okay, so we got 5 moles of nitrogen, 8 moles of oxygen, and the total pressure, I'm going to write it P total, it says the total pressure is 760 torr.
Could you please move your paper up a little bit? We can't really see.
Oh,
Thank
you
so
don't,
much.
yeah, there it goes, okay. Yeah, thank you. So the problem has 5 moles of nitrogen, 8 moles of oxygen with a total pressure of 760. And we want to know what's the partial pressure, P of N2, in that mixture. What is it? Okay, this is going to be a Raoult's law problem because we're giving a number of moles and all this kind of stuff. And so the pressure of the nitrogen would be the mole fraction of the nitrogen times the total pressure. Okay, so this is going to be kind of a plug and chug. We first got to get the mole fraction of nitrogen. Mole fraction of nitrogen is going to be the moles of nitrogen divided by the total moles. There's just 2, so it's moles of nitrogen and moles of oxygen. And so the mole fraction is going to be the moles of nitrogen is 5. Moles of nitrogen is 5. Moles of oxygen was 8. So that's going to be the, this plus 8, not times, plus 8. 5 divided by 5 plus 8 is 13. So that's going to be the mole fraction. There's 5 moles of nitrogen and 13 total. So I take 5 divided by 13. 5 divided by 13, this comes out to be 0.3846 and a whole bunch of digits. So the partial pressure of the nitrogen, N2, is the mole fraction, the 0.3846 and digits, multiplied by the total pressure is 760 torr. Okay, so if I just take that number times 760, I get, I'll write it here in this white space, the pressure of the N2 is 292.30769, another digit or 2, torr. I don't know it's torr, but that's, mole fraction has no units. Moles over moles cancels out. So there's no units. So when I do this multiplication, the answer is going to have the same unit that this was given in. And I gave it in torr. I could have done it in atmospheres. I could have done it kilopascals. I could do anything I want to. Whatever unit I put in for the total pressure, that'll be the unit for the partial pressure of nitrogen. And we get, I guess, 3 significant figures. I'm counting these as counters. So I'm saying exactly 5 moles, exactly 8 moles. So I'm not counting one significant figure. The 760 torr, I'm giving that as a 3 significant digit number. So the answer ought to be 3. So it ought to be there, 292. And that is response B on the test. Okay. One more to go and we'll be finished. And of course, we saved the best one to last. All right. The van der Waals problem. Use the van der Waals equation to calculate the pressure exerted by 24.5 grams of ammonia, and there's the A and B constant confined to a 2.15 liter container at 300 degrees Celsius, and the answer is given in pascals. So here we go. Number 7, van der Waals equation, P plus A n squared over V squared times V minus NB equals nRT. And I want to solve for pressure. Okay, so let's do the math. I'm going to get rid of this term by dividing both sides by it, V minus NB. When I do that, these terms are gone. Now I want to get rid of the AN squared over V squared, so I'm going to subtract AN squared over V squared from both sides. When I do that, subtracting that from the same thing, it goes away, and now I've got pressure by itself. Pressure is going to be nRT over V minus NB minus A n squared over B squared. Okay, so now we've got everything set up. So let's do the values. I've got 24.5 grams of ammonia. Now you have to know ammonia is NH3. I want to convert that then from grams to moles. 1 mole of the compound has 1 nitrogen and 3 hydrogens, so that's going to be 14.01 plus 3 times hydrogen is 1.008. 797, yeah, 8. That's okay. Carrying one more extra significant figure there than I need. That's what I wanted to do. Okay, so let's do this part of the math. I'm taking 24.5. I want to divide it by the sum of these things, 14.01 plus 3 times 1.008, right. Okay, so what I've got is this divided by its molecular weight, and now this is coming out to be my N. My N is going to be 1.4382998 and some more digits, moles of, that's what's going in here and here. Let's remind ourselves what the constants are. R is 0.0821. The temperature. Temperature is 300 Celsius, so that's 300 plus 273.15. I'll go ahead and put that on. So that's going to be what, 573.15 kelvins. Okay, so I've got the temperature. R and the T, the volume. The volume is 2.15 liters. That's the right unit. I need the liter unit because R is in liter atmospheres per mole per Kelvin. So I have to have the volume in liters, I have to have pressure in atmospheres, and I have to have temperature in kelvins. And so that's, we have that so far. Let's see, what else do I need? I got the temperature, volume, and R. My A and B constants. A is 4.3044 for ammonia, and B for ammonia is 0.03 7847. Okay, so now I've got all my data in there. So let's go ahead and do just exactly what this says. Okay, now this is a case where I've already got n in my calculator. I don't want to round it off. I want to use the number I have. So I've got that in my calculator. I need to multiply it by r. So I just say times r is 0.0821. I want to multiply it by t times 573.15. I want to divide it by a left parenthesis. The volume is 2.15. 2.15 minus n, that's answer, second answer, n times b. And the b constant is 0.037847. Now I'm right there. I need to close that parenthesis. And now I need to subtract. A is 4.3044, 4.3044 times n is in my answer key, so second answer squared. That's got an squared, and then I want to divide it by v squared 2.15 squared. Now, if I didn't screw up somewhere, this ought to come out exactly right. I haven't rounded off anything. I'm ready to get the answer and round off the answer. Okay, so I'm going to push equal and see what I come out with. All right, what I came out with on my calculator, it says P is equal to 30.377758. Now, what's the unit? Atmospheres. And when I'm doing any one of these equations, the first pressure unit I'm going to get is atmospheres because I'm going to use R as 0.0821. I don't remember what the value of R is in pascals or kilopascals or some other pressure unit. But I do remember what it is when I'm using atmospheres as pressure unit. So when I set up the problem, my number on my calculator has the unit of atmospheres. I'm looking at the answers. They are pascals. And the conversion is 1 atmosphere, that's the 3 significant figures, is 101.3 kilopascals, that's 10 to the third, pascals. So I need to multiply that by 101.3 times 10 to the third. So I take that answer, times 101.3 exponent 3, and that should give me my answer. So what I got is my calculator showing 3.07652.379 pascals. And that's 1, 2, 3, 4, 5, 6. What have I got? 1, 2, 3, 4, 5, 6. So it's this would be times 10 to the 6 pascals if I write it just 3.0. My calculator is showing 3076529 point. So 1, 2, 3, 4, 5, 6. It should be 3.076 times 10 to the 6. And rounding off to 3 significant figures would be 3.08. Pascals. And that's response A. Okay. So it looks messy, but if you get this set up right, if you solve for P correctly, then all you've got to do is plug the numbers in and plug them in the equation you got right there. And we did our first calculation, we got moles, and then I didn't round that off to 1.4 or 1.44 or 1.438. I didn't round that off anywhere. I left it as it is. It was on my calculator register, so it allowed me to plug it in here and here and here without having to retype the numbers in. And in my own case, if I typed those numbers in 3 times, I would be very, very lucky if I typed them in correctly all 3 times. I just don't want to do that. Okay, all righty. Now that is all there is. There is one more question on your quiz, but again, it should be something that we've talked about in lecture and emphasized, and it shouldn't be a surprise to you when you see it. Couple of things you do need to notice. I didn't give you nomenclature per se on this quiz, except I told you ammonia, didn't give you the formula. I did give you the formulas on all the compounds and the equations, so that's okay. I didn't give you chloric acid, so you had to know the formula for chloric acid in order to solve number 2. And so I've not got a separate nomenclature question, but in fact, nomenclature is on the quiz because you'll need to know how to write some formulas that you might need to use in solving the problems. Okay. All right. So that's what your quiz would look like. And I'm going to